Welcome to this introductory course on data engineering, the first in a series of courses designed to prepare you for a career as a junior data engineer. Data is growing at an unprecedented rate, and so are the ways in which data is being tapped by businesses, industries, institutions, and governments all over the world for making decisions that guide their future and the future of the people they serve. How much value we derive from data really depends on just two things: the accuracy of data and the efficiency with which we're able to access the data we need when we need it. That, in a nutshell, is the job of a data engineer. And the opportunity is huge. Dice Tech Job Report of 2020 lists data engineering as the fastest growing tech occupation with year-over-year growth of 50%. This course is for you if you want to become a data engineer. You may have a background in engineering or computer science. You may be a graduate from a non-related stream, or you may be a non-graduate who loves coding. You can start your journey on this path by taking this course. You may even be a data professional who is excited about engineering, or a working professional with a technical role. In whichever capacity, this course will help you upskill and gain an opportunity in this field. This course introduces you to the core concepts, ecosystem, and life cycle of data engineering. You will learn about data, data repositories, data pipelines, data integration platforms, and big data. You will also learn about the architecture of a data platform, the design considerations for a data store, how to extract, transform, and clean data to make it ready for analytics, and the principles of data security, privacy, and compliance regulations. At different points through the course, you will hear from a panel of subject matter experts and practitioners sharing their knowledge and advising you on possible pathways that can help you become a data engineer.
Hi, I'm Rav Ahuja. I'm a computer engineer by education, a data engineer by training, and I currently lead the content and strategy team for IBM Skills Network.
My name is Ember Crooks, and I have been a data professional for about 20 years now. I started my career with databases straight out of college with IBM. I was a DB2 database administrator. Currently, I am a lead database engineer for an organization that does a lot of work with DevOps.
I am Ramesh Sanareddy. I am the CEO of a company called Mongo Factory. At Mongo Factory, we provide data engineering consulting.
My name is Xiaoyang. I'm a data engineer at Coursera.
Hi, my name is Raghu Cherkuru. I work as a lead database administrator for a large retailer out here in the Midwest. Today we are going to talk about data engineering.
We are very excited to bring this course to you. Congratulations on choosing to be on this journey, and good luck. To quote a Forbes 2020 report on data in the coming decade, the constant increase in data processing speeds and bandwidth, the nonstop invention of new tools for creating, sharing, and consuming data, and the steady addition of new data creators and consumers around the world ensure that data growth continues unabated. Data begets more data in a constant virtuous cycle. A modern data ecosystem includes a whole network of interconnected, independent, and continually evolving entities. It includes data that has to be integrated from disparate sources, different types of analysis and skills to generate insights, active stakeholders to collaborate and act on insights generated, and tools, applications, and infrastructure to store, process, and disseminate data as required. Let's start with the data sources. Data is available in a variety of structured and unstructured data sets, residing in text, images, videos, clickstreams, user conversations, social media platforms, the Internet of Things or IoT devices, real-time events that stream data, legacy databases, and data sourced from professional data providers and agencies. The sources have never before been so diverse and dynamic. When you're working with so many different sources of data, the first step is to pull a copy of the data from the original sources into a data repository. At this stage, you're only looking at acquiring the data you need, working with data formats, sources, and interfaces through which this data can be pulled in. Reliability, security, and integrity of the data being acquired are some of the challenges you work through at this stage. Once the raw data is in a common place, it needs to get organized, cleaned up, and optimized for access by end users. The data will also need to conform to compliances and standards enforced in the organization. For example, conforming to guidelines that regulate the storage and use of personal data such as health, biometrics, or household data in the case of IoT devices. Adhering to master data tables within the organization to ensure standardization of master data across all applications and systems of an organization is another example. The key challenges at this stage could involve data management and working with data repositories that provide high availability, flexibility, accessibility, and security. Finally, we have our business stakeholders, applications, programmers, analysts, and data science use cases all pulling this data from the enterprise data repository. The key challenges at this stage could include the interfaces, APIs, and applications that can get this data to the end users in line with their specific needs. For example, data analysts may need the raw data to work with. Business stakeholders may need reports and dashboards. Applications may need custom APIs to pull this data. It's important to note the influence of some of the new and emerging technologies that are shaping today's data ecosystem and its possibilities. For example, cloud computing, machine learning, and big data, to name a few. Thanks to cloud technologies, every enterprise today has access to limitless storage, high-performance computing, open-source technologies, machine learning technologies, and the latest tools and libraries. Data scientists are creating predictive models by training machine learning algorithms on past data. Also, big data. Today, we're dealing with datasets that are so massive and so varied that traditional tools and analysis methods are no longer adequate, paving the way for new tools and techniques and also new knowledge and insights. We'll learn more about big data and its influence in shaping business decisions further along in this course. Today, organizations that are using data to uncover opportunities and are applying that knowledge to differentiate themselves are the ones leading into the future. Whether looking for patterns in financial transactions to detect fraud, using recommendation engines to drive conversion, mining social media posts for customer voice, or brands personalizing their offers based on customer behavior analysis, business leaders realize that data holds the key to competitive advantage. To get value from data, you need a vast number of skill sets and people playing different roles. In this video, we're going to look at the role data engineers, data analysts, data scientists, business analysts, and business intelligence or BI analysts play in helping organizations tap into vast amounts of data and turn them into actionable insights. It all starts with a data engineer. Data engineers are people who develop and maintain data architectures and make data available for business operations and analysis. Data engineers work within the data ecosystem to extract, integrate, and organize data from disparate sources, clean, transform, and prepare data, design, store, and manage data in data repositories. They enable data to be accessible in formats and systems that the various business applications, as well as stakeholders like data analysts and data scientists, can utilize. A data engineer must have good knowledge of programming, sound knowledge of systems and technology architectures, and in-depth understanding of relational databases and non-relational data stores. Now let's look at the role of a data analyst. In short, a data analyst translates data and numbers into plain language so organizations can make decisions. Data analysts inspect and clean data for deriving insights, identify correlations, find patterns, and apply statistical methods to analyze and mine data, and visualize data to interpret and present the findings of data analysis. Analysts are the people who answer questions, such as, are the user's search experiences generally good or bad with the search functionality on our site? Or what is the popular perception of people regarding our rebranding initiatives? Or is there a correlation between sales and one product and another? Data analysts require good knowledge of spreadsheets, writing queries, and using statistical tools to create charts and dashboards. Modern data analysts also need to have some programming skills. They also need strong analytical and storytelling skills. And now let's look at the role data scientists play in this ecosystem. Data scientists analyze data for actionable insights and build machine learning or deep learning models that train on past data to create predictive models. Data scientists are people who answer questions such as, how many new social media followers am I likely to get next month? Or, what percentage of my customers am I likely to lose to competition in the next quarter? Or, is this financial transaction unusual for this customer? Data scientists require knowledge of mathematics, statistics, and a fair understanding of programming languages, databases, and building data models. They also need to have domain knowledge. Then we also have business analysts and BI analysts. Business analysts leverage the work of data analysts and data scientists to look at possible implications for their business and the actions they need to take or recommend. BI analysts do the same, except their focus is on the market forces and external influences that shape their business. They provide business intelligence solutions by organizing and monitoring data on different business functions and exploring that data to extract insights and actionables that improve business performance. To summarize in simple terms, data engineering converts raw data into usable data. Data analytics uses this data to generate insights. Data scientists use data analytics and data engineering to predict the future using data from the past. Business analysts and business intelligence analysts use these insights and predictions to drive decisions that benefit and grow their business. Interestingly, it's not uncommon for data professionals to start their career in one of the data roles and transition to another role within the data ecosystem by supplementing their skills. In this video, we will further explore the scope of data engineering within the modern data ecosystem. In the simplest possible terms, the field of data engineering concerns itself with the mechanics for the flow and access of data, and its goal is to make quality data available for fact-finding and data-driven decision-making. As data has grown, so has the field of data engineering. From data being available in a single database that was relatively easier to manage, the world of data has grown to include wide-ranging sources, structures, and types of data. The field of data engineering concerns itself with the tasks of collecting source data, processing data, storing data, and making data available to users securely. Collecting source data, including extracting, integrating, and organizing data from disparate sources. To collect required data, you need to develop tools, workflows, and processes that help you acquire data from multiple sources. as well as design, build, and maintain scalable data architecture to store data. Data could be stored in databases, data warehouses, data lakes, or any other type of data repository. Processing data includes cleaning, transforming, and preparing data so that it is usable. For this, you need to implement and maintain distributed systems for large-scale processing of data. Design pipelines for extraction, transformation, and loading of data into data repositories. Design or implement solutions for validating and safeguarding quality, privacy, and security of data. Optimize tools, systems, and workflows for performance, reliability, and scalability, and ensure data meets all regulatory and compliance guidelines. Storing data for reliability and easy availability of data. For this, you need to architect or implement data stores for the storage of processed data. Ensure systems are scalable, keeping in mind the evolving nature of data and business needs. And ensure tools and systems are in place that take care of data privacy, security, compliance, monitoring, backup, and recovery. And finally, making data available to users securely. This includes the use of APIs, services, and programs that retrieve data on defined parameters for use by end users. Interfaces and dashboards that present data to users so they can derive insights from the data. And ensure the right measures and checks and balances are in place to keep data secure and provide rights-based access to users. It is important to mention that data engineering is a team sport. No one person is expected to have all the knowledge, skills, and specializations required for the wide-ranging tasks covered within the scope of data engineering. For example, to architect any data management system, be it for collecting source data or storing processed analysis-ready data, you need to have the skills of an architect. To ensure data stores are available and optimized for use, you need to have expertise in databases. Similarly, proficiency in database tools, programming languages, and distributed systems all come under data engineering, but they may require different skill sets. Also, not all teams and organizations need to set up an end-to-end data engineering practice. There are tools, applications, and solutions available in the market, both on-premise and cloud-based, that can be evaluated for individual needs. In this video, we learned how data engineering works to provide a robust and scalable structure to make quality data available for decision-making. More than any other data profession, data engineering is about the tools and technologies involved in data manipulation. But it is also about understanding the complexities of data and how it is ultimately leveraged for fact-finding and decision-making. In this video, we will listen to several data professionals talk about how they define data engineering and how it differs from data analytics and data science.
Data engineering is the tasks of designing, building, maintaining data infrastructures and platforms. These data infrastructures can include databases, big data repositories, as well as data pipelines for transforming and moving data between these systems. So a data engineer is someone who performs these tasks of developing and optimizing data systems and make data available for analysis. Whereas a data analyst is someone who analyzes data in these systems to report and derive insights. And a data scientist takes this even further by performing deeper analysis on the data and developing predictive models to solve more complex data problems.
As data engineers, we are kind of the plumbers of data. We make sure that the data is highly available. We make sure that the data is consistent. We make sure that the data is secure, and we make sure that the data is recoverable. We don't spend as much time playing with the data or analyzing the data or actually using the data as we do making sure it's ready for others to do those jobs. A lot of times data science and data analytics will make use of the data that we store. It's also a scenario where we work closely with other data professionals to make sure that the data matches their needs and it is available in a way that actually helps them.
Data engineering is all about designing, maintaining, and optimizing systems that will help enterprises and companies make the most of their data. When we get into specifics, it's all about choosing the right databases, the right storage systems, the right cloud architectures or cloud platforms, so that when we put together all these things, the data flow inside an organization is seamless and data can be delivered to whoever needs it at whatever time with minimal effort and as soon as possible. In an ideal organization with the best data engineering processes, anybody can get access to any data that he or she is authorized to in a split second time. Now, if you talk about data analysts and data scientists, their work can be thought of as an upstream work. That is, after the job of a data engineer finishes and the data is made available, then data analysts and data scientists can make use of that data to work out their analysis and come up with their predictions.
Data engineers extract and collect raw data from multiple sources, transform them and store them in queryable forms. While data scientists or data analysis, they perform analysis on top of the data that's prepared by data engineering and try to get business insights from those data.
You can think of data engineering as a precursor to the data analysis and data science. Data engineers act as enablers and make the data projects of data analysts and data scientists materialize into reality. For example, they can assist the data analysts and data scientists with picking the right databases and tools, and by building the required data pipelines to help with their data needs and build their reports and perform statistical analysis.
In this video, we will listen to several data professionals talk about how data engineering has evolved over the past couple of decades.
Compared to 2 decades back, the data engineering eco space or landscape is a totally different one. It's almost unrecognizable compared to what it was 2 decades back. If you look at today's scenario, the sheer quantity of data that we handle today was unthinkable 2 decades back. We also handle with a variety of data and data formats which probably didn't even exist 2 decades back. And 2 decades back, we were not talking about the concept of NoSQL databases, but today we work with a variety of NoSQL databases. And 2 decades back, big data was unheard of, whereas today it is pretty much stable to many enterprises and organizations. One of the major difference that I see between before two decades and now is the expectations from data engineering. They have grown a lot. Today, when a data engineer is given a job, the turnaround time is a lot less. Earlier, we could take days to come back with a solution, but today the expectation is that, okay, we come back with a solution within hours. And today you cannot run a complete data engineering service without the use of automation tools. So you need a lot of automation tools to make sure that we deliver the data engineering service to the organization.
So I started off in this field almost 25 years ago, and there's been a significant evolution in technology in general, but specifically as data and data technologies and systems are concerned. So for example, with cloud computing, data infrastructure is now available as a service. So a data engineer today needs to do a lot less from scratch. They can spend more time on doing things that matter and less time on setting up and managing these systems. So when I started off in data engineering, it primarily involved using relational databases and data warehouses. Now there's a lot of NoSQL databases and other types of data repositories. Another major evolution has been around big data, and data engineers today need to know how to work with several different big data systems and pipelines. And while there are still specializations, today I think a data engineer needs to know about a greater variety of tools and data systems and how they can be effectively used for solving different types of data problems.
So over the past couple of decades, the way that we handle data has changed very significantly. When I started, it was a very hierarchical approach. There was somebody at the top, an architect, an enterprise architect, a data architect, people who decided how we were going to store data within an organization. Usually there were a couple or three supported platforms, and we stuck to those. That was well defined for us. And over the last 20 years, it's been a very gradual transition from that to a situation where it's much more often that the way data is stored comes to us from a developer. A developer wants it stored in a particular way. A developer has specific requirements. So it's interesting to have the requirements coming from a different direction, and that changes our role a little bit. So instead of making sure that we are really great on those 2 or 3 platforms that were previously defined for us, what we have to do now is we have to take these varying sets of requirements and needs from developers and work with those developers to make sure that the choices they're making are appropriate for data operations, for the long-term use of data and storage of data in a secure and reliable way. So it's more of a conversation in how things happen, and it's much more of a learning expedition for the data engineer to go out and figure out what's the best way to do this new thing that the developers need. What's the best way for me to do this and still have that reliable, highly available, secure data platform that is what the organization really needs.
Data engineering evolved tremendously in the past couple of decades. When I started 15 years ago as a database administrator, data engineering was not that hot topic. There were data engineers, but it's a full-on, very hot requirement these days. So the reason for this is it's basically the evolution of different kinds of data sources. For example, now we have Internet of Things, related data, all these sensors related information being fed into these various kinds of data sources, and API feeds from Twitter, weather APIs, you name it, and everything interconnected. As a result, the need for a variety of data sources evolved. So for example, you have relational databases from for a long time, for maybe 4 or 5 decades. Now you have column stores, wide column stores like Cassandra or HBase, and key value pair databases, Hadoop for big data, document stores like MongoDB or Couchbase. So as a data engineer, you need to be familiar with all these kinds of data sources. With the evolution of data sources and the variety of the data engineering role evolved significantly over the past couple of decades.
I have only worked in data engineering for 2 years, so I can only share what I have learned or I have observed during the past 2 years. I think traditionally data engineering focuses a lot on database management, ETL pipelines, and data visualization. While in recent years, I have seen a lot of more and more demand for data engineering to understand distributed computing and DevOps, and to implement machine learning models and so on.
In this video, we will learn about the responsibilities and skill sets of a data engineer. The overarching responsibility of a data engineer is to provide analytics-ready data to data consumers. Data is analytics-ready when it is accurate, reliable, complies to regulations it is governed by, and is accessible to consumers when they need it. At a broad level, data engineers extract, organize, and integrate data from disparate sources. Prepare data for analysis and reporting by transforming and cleansing it. Design and manage data pipelines that encompass the journey of data from source to destination systems. And set up and manage the infrastructure required for the ingestion, processing, and storage of data. This can include data platforms, data stores for aggregating source data, distributed systems for large-scale processing of data, and data repositories for storage and dissemination of analysis-ready data. Next, we'll learn about some of the technical, functional, and soft skills you may need as a data engineer. Let us begin with the technical skills. These include knowledge of working with operating systems such as Unix, Linux, and Windows, including commonly used administrative tools, system utilities, and commands. Knowledge of infrastructure components, such as virtual machines, networking, and application services, such as load balancing and application performance monitoring. Also, cloud-based services, such as those offered by Amazon, Google, IBM, and Microsoft. Experience of working with databases and data warehouses, which include RDBMSs such as IBM DB2, MySQL, Oracle Database, and PostgreSQL. NoSQL databases such as Redis, MongoDB, Cassandra, and Neo4j, and data warehouses such as Oracle Exadata, IBM DB2 Warehouse on Cloud, IBM Netezza Performance Server, and Amazon Redshift. A high level of proficiency working with data pipelines. Popular data pipeline solutions include Apache Beam, Airflow, and Dataflow. Experience of working with ETL tools such as IBM InfoSphere Information Server, AWS Glue, and Imprivado. Proficiency in languages for querying, manipulating, and processing data. This includes query languages for accessing and manipulating data in a database, such as SQL for relational databases and SQL-like query languages for NoSQL databases. Programming languages such as Python, R, and Java, and shell and scripting languages such as Unix/Linux Shell and PowerShell. And finally, familiarity with big data processing tools such as Hadoop, Hive, and Spark. The data engineering process involves several different tools and technologies. Having a working knowledge of comparable technologies can help you evaluate the trade-offs between different tools and make appropriate recommendations. Data engineering is at the intersection of software engineering and data science. In addition to the tools and technologies that data engineers use on a daily basis, they also need to have a keen understanding of how data scientists, analysts, and business users leverage analysis-ready data. Some of the functional skills that will serve you as a data engineer include the ability to convert business requirements into technical specifications, the ability to work with the complete software development lifecycle, which includes ideation, architecture, design, prototyping, testing, deployment, and monitoring, an understanding of data's potential application in business, and an understanding of the risks of poor data management, which essentially covers data quality, privacy, security, and compliance. Data engineering is a team sport. You could have multiple data engineers bringing in their specialization to collaborate on a project, closely interacting with the data consumers, which includes the analysts, data scientists, business users, and other technical teams. Therefore, interpersonal skills, teamwork, and collaboration are essential for data engineers. As a data engineer, you need to be able to communicate effectively with both technical and non-technical stakeholders in a manner that a clear understanding can be established. In this video, you learned about some of the responsibilities and skill sets of a data engineer. Data engineering requires a broad set of skill sets. No one data engineer can possibly master each one of these skills, which means you essentially need to select one or more specialization areas, but have a good understanding of all areas so that you can make more informed decisions. Your skills will grow over time, with experience, the areas you choose to focus on, and the time you invest in upskilling yourself. In the first part of this video, we will listen to data professionals talk about some of the technical skills required to be a successful data engineer.
Data engineering is a very fast evolving technology, and obviously you need to love data, otherwise you shouldn't be a data engineer. From coming to technical skills, it really depends on what a data engineer needs or requires to fulfill a particular job role. For example, if you're working in retail, you may need one skill set. For example, they may look for experience with relational databases and Cassandra or Google Big Table kind of architecture related knowledge, because they try to build a 365 by 24 by 7 applications and also build pipelines using Kafka streams and WebSphere MQ to perform some back office processing of the transactional data. And then if you're working in healthcare, you may need a different skill set. If you're working in social media, like Twitter or Facebook, you would need different kinds of skill set. So data engineering is a very wide topic. So given the job role, the requirements vary.
Technical is actually the easy part because you can learn a new technology, you can figure out new things. It's important that you have the basic theory behind data structures and how to work with data. If you don't enjoy change, if you don't enjoy learning, data engineering is not the right place for you. There's a lot of change in any data field, and you have to be willing to roll with that change.
You need to have good networking skills about both LAN and then the WAN. And you need to be good at understanding different kind of storages, the local storage as well as the cloud storage. And you need to have a very good knowledge of operating systems. And then you should be an expert at databases, both RDBMS databases and the NoSQL databases. Programming knowledge is very, very helpful. Any language, Java, C, or Python would be a very great value add. And in today's data engineering landscape, automation is a very, very good skill to have.
In terms of technical skills, a data engineer needs to work with one or more programming languages, operating systems, and have a knowledge of IT infrastructure and landscape. So this includes computer architecture, cloud, virtual machines, containers, and different types of storage and how to work with them. And a data engineer needs to be very proficient at SQL and needs to have a working knowledge with one or more databases, both relational and NoSQL. And it's not needed to get started, but it's very useful to have knowledge and experience of the bigger data engineering ecosystem, which includes ETL, data pipelines, data warehouses, data lakes, and other big data systems.
Different companies have different requirements for their data engineers. Even within the same company, the requirement, the skills required for each data engineer may change over time as the team grows. But in general, in my opinion, there are 4 essential technical skills for data engineers. They are SQL, data modeling, ETL methodologies, and programming skills like Python.
In the second part of this video, we will listen to data professionals talk about some of the qualities and soft skills required to be a successful data engineer.
So to become a data engineer and be successful at it, you need to enjoy problem solving and troubleshooting. You need to be good at teamwork, collaboration, and communication. And it's good to be, being good at logic and having an interest in coding is very useful.
From a data engineer, from a non-technical perspective, we expect a data engineer to be a problem solver, and we want him or her to have very good communication skills, as a data engineer is constantly involved with multiple teams. So it helps if he's a good communicator.
You should be very curious, and you should be able to ask a lot of questions to the business users and technical users, and then use that knowledge from those answers to build robust data pipelines using reliable data sources and suitable data pipelines.
My saying has always been, whether working as a DBA or a data engineer, the best one is a detail-oriented control freak. And that's because there is a lot of detail involved in working with data. It's important to really be comfortable with the details and get into the details and make sure that you don't leave any of the boxes unchecked. Control freak because my data environment, that's my baby. That's what I spend as much time with as my children sometimes. And so that's something where I need to be in control or aware of the choices that are being made there and what trade-offs those particular choices have. The most important skills are soft skills. You need to be able to interact with developers. You need to be able to defend your choices to management. You need to be able to advocate for the choices that you're making and the details of those choices and why they are important and why things need to be done in a particular way. So those things and a work ethic and a passion to learn are the most important things.
Curiosities, good communication, and eagerness to learn are pretty critical for data engineers.
Hi, I'm Sarah Flinch. I work as a data engineer in a multinational company that makes hair care products. Our products are backed by scientific research and rigorous testing and are known to have revolutionized hair care over the past couple of decades. As a company, we are always investing in technologies and practices that can help us be connected to our customers and demographics. Currently, our company is in the final stages of launching a new shampoo in the market. In today's times, how a product gets talked about on social media has an immediate impact on sales numbers and brand perception. So it makes perfect sense that the business team, even before the product is launched, is figuring out how they can tune in to customer sentiment from day one of the launch. They want to keep a close eye on all social media and know what online communities such as Twitter, Facebook, Instagram, e-commerce platforms, and bloggers say about their product. Positive feedback, negative comments, suggestions, even comparisons with their current favorites. Our team of data scientists created the prototype of a dashboard using a sentiment analysis algorithm and dummy data to serve this goal. The dashboard displayed graphs of different customer sentiments plotted as scores across social media sources and consumer demographics. The idea was an instant hit and got a go-ahead for implementation by the business team. This is where our team of data engineers stepped in to make this prototype a reality. My first task was to pull in data from all the social media sites and online sources identified by the business teams into the organization's environment. I started with APIs to pull the tweets and posts with our product's hashtag into temporary storage. I then turned to the e-commerce portals and product review blogs to collect our product-specific data and move that into temporary storage as well, an activity known as web scraping. Tweets, posts, comments, articles, even memes. There was quite a mix of formats and structures. Once I had all the data I needed, I inspected it to assess the transformations that will need to be performed on this data before it can be loaded into the database. We decided to create a Python program for processing the data and loading it into the database. I cleaned up the data and transformed it into a format that would be stored in the database. This is the database from which the dashboard is pulling the data to display the reports. Now it's time to showcase the results to the data scientists. It's exactly what they'd hoped to see, so it's a job well done. But the job doesn't quite end here. Each time the business users need to see the current statistics, they will have to come back to us with a request to pull in the updated data. That would make it an inefficient solution. Ideally, they should be able to tune into customer sentiment and brand perception in real time. So, the next action is for us to build a data pipeline that extracts, transforms, and loads the data on an ongoing basis. Once this process is in place, business teams will be able to see a real-time projection each time they log into the dashboard.
A data engineer's ecosystem includes the infrastructure, tools, frameworks, and processes for extracting data from disparate sources, architecting and managing data pipelines for transformation, integration, and storage of data, architecting and managing data repositories, automating and optimizing workflows and flow of data between systems, and developing applications needed through the data engineering workflow. Let us look at data first. Based on how well defined the structure of data is, data can be categorized as structured, semi-structured, or unstructured. Data that follows a rigid format and can be organized neatly into rows and columns is structured data. This is the data that you see typically in databases and spreadsheets, for example. Semi-structured data is a mix of data that has consistent characteristics and that doesn't conform to a rigid structure. For example, emails. An email has a mix of structured data, such as the name of the sender and recipient, but also has the contents of the email, which is unstructured data. And then there is unstructured data. Data that is complex and mostly qualitative information that is impossible to reduce to rows and columns. For example, photos, videos, text files, PDFs, and social media content. The type of data drives the kind of data repositories that the data can be collected and stored in, and also the tools that can be used to query or process the data. Data also comes in a wide-ranging variety of file formats being collected from a variety of data sources, ranging from relational and non-relational databases to APIs, web services, data streams, social platforms, and sensor devices. A data engineer's ecosystem also includes data repositories. There are two main types of data repositories, transactional and analytical. Transactional systems, also known as online transaction processing or OLTP systems, are designed to store high-volume day-to-day operational data, such as online banking transactions, ATM transactions, and airline bookings. While OLTP databases are typically relational, they can also be non-relational. Analytical systems, also known as online analytical processing or OLAP systems, are optimized for conducting complex data analytics. These include relational and non-relational databases, data warehouses, data marts, data lakes, and big data stores. The type, format, sources of data, and context of use influence which data repository is ideal. Once data from disparate sources has been collated, it needs to be processed, cleansed, and integrated so that it can be accessed via a single interface by users. Data integration tools combine data from disparate sources into a unified view, accessed by users to query and manipulate the data. This brings us to data pipelines, a set of tools and processes that cover the entire journey of data from source to destination systems. Data is integrated within a pipeline using processes such as the extract, transform, and load process, or the extract, load, and transform process. The ecosystem also includes languages that can be classified as query languages, programming languages, and shell and scripting languages. From querying and manipulating data with SQL to developing data applications with Python and writing shell scripts for repetitive operational tasks, these are important components in a data engineer's workbench. BI and reporting tools are used to collect data from multiple data sources and present them in a visual format, such as interactive dashboards. Using these tools, you can connect and visualize your data in real time and on a predefined schedule. These are drag-and-drop products that do not require the users to know any programming. While these tools are typically used by data and BI analysts, they are enabled and managed by data engineers. Automated tools, frameworks, and processes for all stages of the data analytics process are part of the data engineer's ecosystem. It's a diverse, rich, and challenging ecosystem. Further on in the course, we will explore the different parts of this ecosystem in greater detail. Data is unorganized information that is processed to make it meaningful. Generally, data comprises of facts, observations, perceptions, numbers, characters, symbols, and images that can be interpreted to derive meaning. One of the ways in which data can be categorized is by its structure. Data can be structured, semi-structured, or unstructured. Structured data has a well-defined structure or adheres to a specified data model, can be stored in well-defined schemas such as databases, and in many cases can be represented in a tabular manner with rows and columns. Structured data is objective facts and numbers that can be collected, exported, stored, and organized in typical databases. Some of the sources of structured data could include SQL databases and online transaction processing, or OLTP, systems that focus on business transactions, spreadsheets such as Excel and Google Sheets, online forms, sensors such as global positioning systems, or GPS, and radio frequency identification, or RFID tags, and network and web server logs. You can also easily examine structured data with standard data analysis tools and methods. Semi-structured data is data that has some organizational properties but lacks a fixed or rigid schema. Semi-structured data cannot be stored in the form of rows and columns, as in databases. It contains tags or elements or metadata, which is used to group data and organize it in a hierarchy. Some of the sources of semi-structured data could include emails, XML and other markup languages, binary executables, TCP or IP packets, zippered files, and integration of data from different sources. XML and JSON allow users to define tags and attributes to store data in a hierarchical form and are used widely to store and exchange semi-structured data. Unstructured data is data that does not have an easily identifiable structure and therefore cannot be organized in a mainstream relational database in the form of rows and columns. It does not have any particular format, sequence, semantics, or rules. Unstructured data can deal with the heterogeneity of sources and has a variety of business intelligence and analytics applications. Some of the sources of unstructured data could include web pages, social media feeds, images in varied file formats such as JPEG, GIF, and PNG, video and audio files, documents and PDF files, PowerPoint presentations, media logs, and surveys. Unstructured data can be stored in files and documents, such as a Word document, for manual analysis, or in NoSQL databases that have their own analysis tools for examining this type of data. To summarize, structured data is data that is well organized in formats that can be stored in databases and lends itself to standard data analysis methods and tools. Semi-structured data is data that is somewhat organized and relies on meta tags for grouping and hierarchy. And unstructured data is data that is not conventionally organized in the form of rows and columns in a particular format. In the next video, we will learn about the different types of file structures. As a data professional, you will be working with a variety of data file types and formats. It is important to understand the underlying structure of file formats along with their benefits and limitations. This understanding will support you to make the right decisions on the formats best suited for your data and performance needs. Some of the standard file formats that we will cover in this video include delimited text file formats, Microsoft Excel Open XML Spreadsheet, or XLSX, Extensible Markup Language, or XML, Portable Document Format, or PDF, JavaScript Object Notation, or JSON. Delimited text files are text files used to store data as text in which each line or row has values separated by a delimiter, where a delimiter is a sequence of one or more characters for specifying the boundary between independent entities or values. Any character can be used to separate the values, but most common delimiters are the comma, tab, colon, vertical bar, and space. Comma-separated values, or CSVs, and tab-separated values, or TSVs, are the most commonly used file types in this category. In CSVs, the delimiter is a comma, while in TSVs, the delimiter is a tab. When literal commas are present in text data and therefore cannot be used as delimiters, TSVs serve as an alternative to CSV format. Tab stops are infrequent in running text. Each row or horizontal line in the text file has a set of values separated by the delimiter and represents a record. The first row works as a column header, where each column can have a different type of data. For example, a column can be of date type, while another can be a string or integer type data. Delimited files allow field values of any length and are considered a standard format for providing straightforward information schema. They can be processed by almost all existing applications. Delimiters also represent one of various means to specify boundaries in a data stream. Microsoft Excel Open XML Spreadsheet, or XLSX, is a Microsoft Excel Open XML file format that falls under the spreadsheet file format. It is an XML-based file format created by Microsoft. In an XLSX, also known as a workbook, there can be multiple worksheets, and each worksheet is organized into rows and columns, at the intersection of which is the cell. Each cell contains data. XLSX uses the open file format, which means it is generally accessible to most other applications. It can use and save all functions available in Excel and is also known to be one of the more secure file formats as it cannot save malicious code. Extensible Markup Language, or XML, is a markup language with set rules for encoding data. The XML file format is both readable by humans and machines. It is a self-descriptive language designed for sending information over the internet. XML is similar to HTML in some respects, but also has differences. For example, an XML does not use predefined tags like HTML does. XML is platform independent and programming language independent, and therefore simplifies data sharing between various systems. Portable Document Format, or PDF, is a file format developed by Adobe to present documents independent of application software, hardware, and operating systems, which means it can be viewed the same way on any device. This format is frequently used in legal and financial documents and can also be used to fill in data such as forms. JavaScript Object Notation, or JSON, is a text-based open standard designed for transmitting structured data over the web. The file format is a language-independent data format that can be read in any programming language. JSON is easy to use, is compatible with a wide range of browsers, and is considered as one of the best tools for sharing data of any size and type, even audio and video. That is one reason many APIs and web servers return data as JSON. As we touched upon in one of our previous videos, data sources have never been as dynamic and diverse as they are today. In this video, we will look at some common sources such as relational databases, flat files and XML datasets, APIs and web services, web scraping, data streams and feeds. Typically, organizations have internal applications to support them in managing their day-to-day business activities, customer transactions, human resource activities, and their workflows. These systems use relational databases, such as SQL Server, Oracle, MySQL, and IBM DB2 to store data in a structured way. Data stored in databases and data warehouses can be used as a source for analysis. For example, data from a retail transaction system can be used to analyze sales in different regions, and data from a customer relationship management system can be used for making sales projections. External to the organization, there are other publicly and privately available data sets. For example, government organizations releasing demographic and economic data sets on an ongoing basis. Then there are companies that sell specific data. For example, point-of-sale data, or financial data, or weather data, which businesses can use to define strategy, predict demand, and make decisions related to distribution or marketing promotions, among other things. Such datasets are typically made available as flat files, spreadsheet files, or XML documents. Flat files store data in plain text format, with one record or row per line, and each value separated by delimiters such as commas, semicolons, or tabs. Data in a flat file maps to a single table, unlike relational databases that contain multiple tables. One of the most common flat file formats is CSV, in which values are separated by commas. Spreadsheet files are a special type of flat files that also recognize data in a tabular format, rows and columns. But a spreadsheet can contain multiple worksheets, and each worksheet can map to a different table. Although data in spreadsheets is in plain text, the files can be stored in custom formats and include additional information such as formatting, formulas, etc. Microsoft Excel, which stores data in an XLS or XLSX format, is probably the most common spreadsheet. Others include Google Sheets, Apple Numbers, and LibreOffice. XML files contain data values that are identified or marked up using tags. While data in flat files is flat or maps to a single table, XML files can support more complex data structures such as hierarchical. Some common uses of XML include data from online surveys, bank statements, and other unstructured data sets. Many data providers and websites provide APIs, or Application Program Interfaces, and web services, which multiple users or applications can interact with and obtain data for processing or analysis. APIs and web services typically listen for incoming requests, which can be in the form of web requests from users or network requests from applications, and return data in plain text, XML, HTML, JSON, or media files. Let's look at some popular examples of APIs being used as a data source for data analytics. The use of Twitter and Facebook APIs to source data from tweets and posts for performing tasks such as opinion mining or sentiment analysis, which is to summarize the amount of appreciation and criticism on a given subject, such as policies of a government, product, a service, or customer satisfaction in general. Stock market APIs used for pulling data such as share and commodity prices, earnings per share, and historical prices for trading and analysis. Data lookup and validation APIs, which can be very useful for data analysts for cleaning and preparing data, as well as for correlating data, for example, to check which city or state a postal or zip code belongs to. APIs are also used for pulling data from database sources, within and external to the organization. Web scraping is used to extract relevant data from unstructured sources, also known as screen scraping, web harvesting, and web data extraction. Web scraping makes it possible to download specific data from web pages based on defined parameters. Web scrapers can, among other things, extract text, contact information, images, videos, product items, and much more from a website. Some popular uses of web scraping include collecting product details from retailers, manufacturers, and e-commerce websites to provide price comparisons, generating sales leads through public data sources, extracting data from posts and authors on various forums and communities, and collecting training and testing datasets for machine learning models. Some of the popular web scraping tools include Beautiful Soup, Scrapey, Pandas, and Selenium. Data streams are another widely used source for aggregating constant streams of data flowing from sources such as instruments, IoT devices and applications, GPS data from cars, computer programs, websites, and social media posts. This data is generally time-stamped and also geotagged for geographical identification. Some of the data streams and ways in which they can be leveraged include stock and market tickers for financial trading, retail transaction streams for predicting demand and supply chain management, surveillance and video feeds for threat detection, social media feeds for sentiment analysis, sensor data feeds for monitoring industrial or farming machinery, web-click feeds for monitoring web performance and improving design, and real-time flight events for rebooking and rescheduling. Some popular applications used to process data streams include Apache Kafka, Apache Spark Streaming, and Apache Storm. RSS, or Really Simple Syndication Feeds, are another popular data source. These are typically used for capturing updated data from online forums and news sites where data is refreshed on an ongoing basis. Using a feed reader, which is an interface that converts RSS text files into a stream of updated data, updates are streamed to user devices. In this video, we will learn about some of the languages relevant to the work of data professionals. These can be categorized as query languages, programming languages, and shell scripting. Having proficiency in at least one language in each category is essential for any data professional. Simply stated, query languages are designed for accessing and manipulating data in a database, for example, SQL. Programming languages are designed for developing applications and controlling application behavior, for example, Python, R, and Java. And shell and scripting languages, such as Unix or Linux Shell and PowerShell, are ideal for repetitive and time-consuming operational tasks. In the remaining video, we will examine these languages in greater depth. SQL, or Structured Query Language, is a querying language designed for accessing and manipulating information from, mostly, though not exclusively, relational databases. Using SQL, we can write a set of instructions to perform operations, such as insert, update, and delete records in a database, create new databases, tables, and views, and write stored procedures, which means you can write a set of instructions and call them for later use. Here are some advantages of using SQL. SQL is portable and can be used independent of the platform. It can be used for querying data in a wide variety of databases and data repositories, although each vendor may have some variations and special extensions. It has a simple syntax that is similar to the English language. Its syntax allows developers to write programs with fewer lines than some of the other programming languages using basic keywords such as select, insert, into, and update. It can retrieve large amounts of data quickly and efficiently. It runs on an interpreter system, which means code can be executed as soon as it is written, making prototyping quick and easy. SQL is one of the most popular querying languages. Due to its large user community and the sheer volume of documentation accumulated over the years, it continues to provide a uniform platform worldwide to all its users. Python is a widely used, open-source, general-purpose, high-level programming language. Its syntax allows programmers to express their concepts in fewer lines of code as compared to some of the older languages. Python is perceived as one of the easiest languages to learn and has a large developer community. Because of its focus on simplicity and readability and a low learning curve, it's an ideal tool for beginning programmers. It is great for performing high computational tasks in vast amounts of data, which can otherwise be extremely time-consuming and cumbersome. Python provides libraries like NumPy and Pandas, which eases the task by the use of parallel processing. It has inbuilt functions for almost all of the frequently used concepts. Python supports multiple programming paradigms, such as object-oriented, imperative, functional, and procedural, making it suitable for a wide variety of use cases. Now, let's look at some of the reasons that make Python one of the fastest growing programming languages in the world today. It is easy to learn. With Python, you have the advantage of using fewer lines of code to accomplish tasks, compared to other languages. It is open source. Python is free and uses a community-based model for development. It runs on Windows and Linux environments and can be ported to multiple platforms. It has widespread community support with plenty of useful analytics libraries available. It has several open-source libraries for data manipulation, data visualization, statistics, and mathematics, to name just a few. Its vast array of libraries and functionalities also include Pandas for data cleaning and analysis, NumPy and SciPy for statistical analysis, Beautiful Soup, and Scrapey for web scraping, Matplotlib and Seaborn to visually represent data in the form of bar graphs, histogram, and pie charts, OpenSea for image processing. R is an open-source programming language and environment for data analysis, data visualization, machine learning, and statistics. Widely used for developing statistical software and performing data analytics, it is especially known for its ability to create compelling visualizations, giving it an edge over some of the other languages in this space. Some of the key benefits of R include the following. It is an open-source platform-independent programming language. It can be paired with many programming languages, including Python. It is highly extensible, which means developers can continue to add functionalities by defining new functions. It facilitates the handling of structured as well as unstructured data, which means it has more comprehensible data capability. It has libraries such as ggplot2 and Plotly that offer aesthetic graphical plots to its users. You can make reports with the data and scripts embedded in them. Also, interactive web apps that allow users to play with the results and the data. It is dominant among other programming languages for developing statistical tools. Java is an object-oriented, class-based, and platform-independent programming language originally developed by Sun Microsystems. It is among the top-ranked programming languages used today. Java is used in a number of processes all through data analytics, including cleaning data, importing and exporting data, statistical analysis, and data visualization. In fact, most of the popular framework and tools used for big data are typically written in Java, such as Hadoop, Hive, and Spark. It is perfectly suited for speed-critical projects. A Unix or Linux shell is a computer program written for the Unix shell. It is a series of Unix commands written in a plain text file to accomplish a specific task. Writing a shell script is fast and easy. It is most useful for repetitive tasks that may be time-consuming to execute by typing one line at a time. Typical operations performed by shell scripts include file manipulation, program execution, system administration tasks such as disk backups and evaluating system logs, installation scripts for complex programs, executing routine backups, and running batches. PowerShell is a cross-platform automation tool and configuration framework by Microsoft that is optimized for working with structured data formats such as JSON, CSV, XML, and REST APIs, websites, and Office applications. It consists of a command line shell and scripting language. PowerShell is object-based, which makes it possible to filter, sort, measure, group, compare, and many more actions on objects as they pass through a data pipeline. It is also a good tool for data mining, building GUIs, and creating charts, dashboards, and interactive reports. In this video, we will listen to several data professionals talk about their experience of working with varied data sources and types of data.
So you'd be surprised the different ways that data can come at you. I tend to be a relational database fan, and so I spend a lot of time with SQL. And using the power of SQL to deal with moving data from one place to another, to deal with structuring of data, to deal with all the security details around data. But obviously, that doesn't apply to every scenario, and even when we're dealing entirely in relational databases, we're often moving data from one relational database to another, and especially when we're talking about one vendor to another, that can be challenging. The things that also get in the way tend to be the versioning. So sometimes the feature of something that you want is in a version 2 levels above where you are, or it doesn't work the same way as it did 2 versions ago. So working with multiple data sources is about flexibility. It's about finding the function that works and works with the performance you need. Moving data one time is usually not all that hard as long as we're sub-terabyte, but moving data consistently and continually and in a performant way can cause us to evaluate a lot of different solutions. So we really need to be open to new ideas and looking for new solutions that meet the requirements that we have.
Mostly I work with relational databases. They're extremely flexible and withstood the test of time. However, with the evolution of unstructured data such as logs, documents, XML, and JSON, their reputation as a cure for all of your data problems came under intense scrutiny. And most of data-intensive applications such as IoT and social media applications started to look elsewhere. For example, Google released a white paper back in 2006 called Google Big Table. And that idea quickly caught fire. For example, Cassandra and HBase came out of the same architectural model as the Google Big Table, and they became widely popular databases to solve some of the problems that relational databases fail to solve. For example, relational databases struggle a little bit with heavy write-intensive applications such as IoT or sensor data or social media data, because the B-tree data structures that drive or power these relational databases slows down due to their nature of the random reads and random writes for the heavy write applications.
It's an inevitable part of a data engineer's job to work with a variety of data. You will need to work with standard formats like CSV, JSON, XML, but also you'll need to work with proprietary formats. And you will need to get data in different sources, whether it be relational databases, NoSQL, or big data repositories. You will need to work with data at rest, streaming data or data in motion, and you might not have the skills to work with all of these different types of data sources from day one, but you need to be able to learn as you go and pick up these skills required for the project to work with different data sets, different data formats, and different data sources.
When it comes to the data formats, log data, XML data, JSON, etc., each of them comes with their own challenges. For example, log data is extremely challenging because it's unstructured, and you may need to write your own custom tools to parse the data depending on what you want to look at. Whereas XML was widely popular like a decade ago, especially with the SOAP protocol of the web applications. However, soon the web developers and the corporations discovered that it can be resource intensive, especially memory, because it has both the starting and ending tags. So then JSON came into the picture. They got rid of the ending tags and they looked like a key value pairs, and it saved some resources, and it is now widely used as part of the RESTful APIs. And then even newer versions of the data formats such as Apache Avro were gaining a wide popularity because of the efficiency on how they store the data.
One particular situation where we were converting data from a DB2 database into a SQL Server database, and it was challenging because the way that each of those expect imports and exports to happen is a little bit different. The data was particularly challenging, and that's where a lot of your challenge might come from in these projects, is from the data itself. In this particular case, the data had a lot of different characters in it, so usually we're looking for a character we can use as a delimiter. Oftentimes that's comma delimited, so we can separate our fields using commas. But we also have to think about situations where we have data that has commas in it. How do we properly separate that data? How do we properly define our fields? And in this particular case, we had to use different separators for different tables because every single special character that we could think of was in one of those tables. And the special characters that weren't were sometimes ones we couldn't use for separation, such as the bell character.
A data repository is a general term used to refer to data that has been collected, organized, and isolated so that it can be used for business operations or mined for reporting and data analysis. It can be a small or large database infrastructure with one or more databases that collect, manage, and store datasets. In this video, we will provide an overview of the different types of repositories your data might reside in, such as databases, data warehouses, and big data stores, and examine them in greater detail in further videos. Let's begin with databases. A database is a collection of data or information designed for the input, storage, search and retrieval, and modification of data. And a database management system, or DBMS, is a set of programs that creates and maintains the database. It allows you to store, modify, and extract information from the database using a function called querying. For example, if you want to find customers who have been inactive for 6 months or more, using the querying function, the database management system will retrieve data of all customers from the database that have been inactive for 6 months or more. Even though a database and DBMS mean different things, the terms are often used interchangeably. There are different types of databases. Several factors influence the choice of database, such as the data type and structure, querying mechanisms, latency requirements, transaction speeds, and intended use of the data. It's important to mention two main types of databases here: relational and non-relational databases. Relational databases, also referred to as RDBMSs, build on the organizational principles of flat files, with data organized into a tabular format with rows and columns following a well-defined structure and schema. However, unlike flat files, RDBMSs are optimized for data operations and querying involving many tables and much larger data volumes. Structured Query Language, or SQL, is the standard querying language for relational databases. Then we have non-relational databases, also known as NoSQL, or Not Only SQL. Non-relational databases emerged in response to the volume, diversity, and speed at which data is being generated today, mainly influenced by advances in cloud computing, the Internet of Things, and social media proliferation. Built for speed, flexibility, and scale, non-relational databases made it possible to store data in a schemaless or free-form fashion. NoSQL is widely used for processing big data. A data warehouse works as a central repository that merges information coming from disparate sources and consolidates it through the extract, transform, and load process, also known as the ETL process, into one comprehensive database for analytics and business intelligence. At a very high level, the ETL process helps you to extract data from the different data sources, transform the data into a clean and usable state, and load the data into the enterprise's data repository. Related to data warehouses are the concepts of data marts and data lakes, which we will cover later. Data marts and data warehouses have historically been relational, since much of the traditional enterprise data has resided in RDBMSs. However, with the emergence of NoSQL technologies and new sources of data, non-relational data repositories are also now being used for data warehousing. Another category of data repositories are big data stores that include distributed computational and storage infrastructure to store, scale, and process very large data sets. Overall, data repositories help to isolate data and make reporting and analytics more efficient and credible while also serving as a data archive. A relational database is a collection of data organized into a table structure, where the tables can be linked or related based on data common to each. Tables are made of rows and columns, where rows are the records and the columns the attributes. Let's take the example of a customer table that maintains data about each customer in a company. The columns or attributes in the customer table are the customer ID, customer name, customer address, and customer primary phone, and each row is a customer record. Now, let's understand what we mean by tables being linked or related based on data common to each. Along with the customer table, the company also maintains transaction tables that contain data describing multiple individual transactions pertaining to each customer. The columns for the transaction table might include the transaction date, customer ID, transaction amount, and payment method. The customer table and transaction tables can be related based on the common customer ID field. You can query the customer table to produce reports such as a customer statement that consolidates all transactions in a given period. This capability of relating tables based on common data enables you to retrieve an entirely new table from data in one or more tables with a single query. It also allows you to understand the relationships among all available data and gain new insights for making better decisions. Relational databases use structured query language, or SQL, for querying data. We'll learn more about SQL later in this course. Relational databases build on the organizational principles of flat files, such as spreadsheets, with data organized into rows and columns following a well-defined structure and schema. But this is where the similarity ends. Relational databases, by design, are ideal for the optimized storage, retrieval, and processing of data for large volumes of data, unlike spreadsheets that have a limited number of rows and columns. Each table in a relational database has a unique set of rows and columns, and relationships can be defined between tables, which minimizes data redundancy. Moreover, you can restrict database fields to specific data types and values, which minimizes irregularities and leads to greater consistency and data integrity. Relational databases use SQL for querying data, which gives you the advantage of processing millions of records and retrieving large amounts of data in a matter of seconds. Moreover, the security architecture of relational databases provides controlled access to data and also ensures that the standards and policies for governing data can be enforced. Relational databases range from small desktop systems to massive cloud-based systems. They can be either open source and internally supported, open source with commercial support, or commercial closed source systems. IBM DB2, Microsoft SQL Server, MySQL, Oracle Database, and PostgreSQL are some of the popular relational databases. Cloud-based relational databases, also referred to as database as a service, are gaining wide use as they have access to the limitless compute and storage capabilities offered by the cloud. Some of the popular cloud relational databases include Amazon Relational Database Service, or RDS, Google Cloud SQL, IBM DB2 on Cloud, Oracle Cloud, and SQL Azure. RDBMS is a mature and well-documented technology, making it easy to learn and find qualified talent. One of the most significant advantages of the relational database approach is its ability to create meaningful information by joining tables. Some of its other advantages include flexibility. Using SQL, you can add new columns, add new tables, rename relations, and make other changes while the database is running and queries are happening. Reduced redundancy. Relational databases minimize data redundancy. For example, the information of a customer appears in a single entry in the customer table, and the transaction table pertaining to the customer stores a link to the customer table. Ease of backup and disaster recovery. Relational databases offer easy export and import options, making backup and restore easy. Exports can happen while the database is running, making restore on failure easy. Cloud-based relational databases do continuous mirroring, which means the loss of data on restore can be measured in seconds or less. ACID compliance. ACID stands for atomicity, consistency, isolation, and durability. ACID compliance implies that the data in the database remains accurate and consistent despite failures, and database transactions are processed reliably. Now we'll look at some use cases for relational databases. Online transaction processing. OLTP applications are focused on transaction-oriented tasks that run at high rates. Relational databases are well suited for OLTP applications because they can accommodate a large number of users. They support the ability to insert, update, or delete small amounts of data. And they also support frequent queries and updates as well as fast response times. data warehouses. In a data warehousing environment, relational databases can be optimized for online analytical processing, or OLAP, where historical data is analyzed for business intelligence. IoT solutions, Internet of Things or IoT solutions, require speed as well as the ability to collect and process data from edge devices, which need a lightweight database solution. This brings us to the limitations of RDBMS. RDBMS does not work well with semi-structured or unstructured data, and is therefore not suitable for extensive analytics on such data. For migration between two RDBMSs, schemas and type of data need to be identical between the source and destination tables. Relational databases have a limit on the length of data fields, which means if you try to enter more information into a field than it can accommodate, the information will not be stored. Despite the limitations and the evolution of data in these times of big data, cloud computing, IoT devices, and social media, RDBMS continues to be the predominant technology for working with structured data. NoSQL, which stands for Not Only SQL, or sometimes non-SQL, is a non-relational database design that provides flexible schemas for the storage and retrieval of data. NoSQL databases have existed for many years, but have only recently become more popular in the era of cloud, big data, and high-volume web and mobile applications. They are chosen today for their attributes around scale, performance, and ease of use. It's important to emphasize that the No in NoSQL is an abbreviation for not only, and not the actual word no. NoSQL databases are built for specific data models and have flexible schemas that allow programmers to create and manage modern applications. They do not use a traditional row, column, table database design with fixed schemas, and typically not use the structured query language, or SQL, to query data, although some may support SQL or SQL-like interfaces. NoSQL allows data to be stored in a schemaless or free-form fashion. Any data, be it structured, semi-structured, or unstructured, can be stored in any record. Based on the model being used for storing data, there are 4 common types of NoSQL databases: key-value store, document-based, column-based, and graph-based. Key-value store. Data in a key-value database is stored as a collection of key-value pairs. The key represents an attribute of the data and is a unique identifier. Both keys and values can be anything from simple integers or strings to complex JSON documents. Key-value stores are great for storing user session data and user preferences, making real-time recommendations and targeted advertising, and in-memory data caching. However, if you want to be able to query the data on specific data value, need relationships between data values, or need to have multiple unique keys, a key-value store may not be the best fit. Redis, Memcached, and DynamoDB are some well-known examples in this category. Document-based. Document databases store each record and its associated data within a single document. They enable flexible indexing, powerful ad hoc queries, and analytics over collections of documents. Document databases are preferable for e-commerce platforms, medical records storage, CRM platforms, and analytics platforms. However, if you're looking to run complex search queries and multi-operation transactions, a document-based database may not be the best option for you. MongoDB, DocumentDB, CouchDB, and Cloudant are some of the popular document-based databases. Column-based. Column-based models store data in cells grouped as columns of data instead of rows. A logical grouping of columns, that is, columns that are usually accessed together, is called a column family. For example, a customer's name and profile information will most likely be accessed together, but not their purchase history. So, customer name and profile information data can be grouped into a column family. Since column databases store all cells corresponding to a column as a continuous disk entry, accessing and searching the data becomes very fast. Column databases can be great for systems that require heavy write requests, storing time series data, weather data, and IoT data. But if you need to use complex queries or change your querying patterns frequently, this may not be the best option for you. The most popular column databases are Cassandra and HBase. Graph-based. Graph-based databases use a graphical model to represent and store data. They are particularly useful for visualizing, analyzing, and finding connections between different pieces of data. The circles are nodes, and they contain the data. The arrows represent relationships. Graph databases are an excellent choice for working with connected data, which is data that contains lots of interconnected relationships. Graph databases are great for social networks, real-time product recommendations, network diagrams, fraud detection, and access management. But if you want to process high volumes of transactions, it may not be the best choice for you, because graph databases are not optimized for large volume analytics queries. Neo4j and Cosmos DB are some of the more popular graph databases. NoSQL was created in response to the limitations of traditional relational database technology. The primary advantage of NoSQL is its ability to handle large volumes of structured, semi-structured, and unstructured data. Some of its other advantages include the ability to run as distributed systems scaled across multiple data centers, which enables them to take advantage of cloud computing infrastructure, an efficient and cost-effective scale-out architecture that provides additional capacity and performance with the addition of new nodes, and simpler design, better control over availability, and improved scalability that enables you to be more agile, more flexible, and to iterate more quickly. To summarize the key differences between relational and non-relational databases, RDBMS schemas rigidly define how all data inserted into the database must be typed and composed, whereas NoSQL databases can be schema agnostic, allowing unstructured and semi-structured data to be stored and manipulated. Maintaining high-end commercial relational database management systems is expensive, whereas NoSQL databases are specifically designed for low-cost commodity hardware. Relational databases, unlike most NoSQL, support ACID compliance, which ensures reliability of transactions and crash recovery. RDBMS is a mature and well-documented technology, which means the risks are more or less perceivable as compared to NoSQL, which is a relatively newer technology. Nonetheless, NoSQL databases are here to stay and are increasingly being used for mission-critical applications. All data mining repositories have a similar goal, which is to house data for reporting, analysis, and deriving insights. But their purpose, types of data stored, and how data is accessed differs. In this video, we will learn about some of the characteristics and applications of data warehouses, data marts, and data lakes. A data warehouse is a central repository of data integrated from multiple sources. Data warehouses serve as the single source of truth, storing current and historical data that has been cleansed, conformed, and categorized. When data gets loaded into the data warehouse, it is already modeled and structured for a specific purpose, meaning it's analysis ready. Traditionally, data warehouses are known to store relational data from transactional systems and operational databases, such as CRM, ERP, HR, and finance applications. But with the emergence of NoSQL technologies and new data sources, non-relational data repositories are also being used for data warehousing. Typically, a data warehouse has a 3-tier architecture. The bottom tier of the architecture includes the database servers, which could be relational, non-relational, or both, that extract data from different sources. The middle tier of the architecture consists of the OLAP server, a category of software that allows users to process and analyze information coming from multiple database servers. And the topmost tier of the architecture includes the client front-end layer. This tier includes all the tools and applications used for querying, reporting, and analyzing data. In response to the rapid data growth and today's sophisticated analytics tools, data warehouses that once resided in on-premise data centers are moving to the cloud. Compared to their on-premise versions, some of the benefits offered by cloud-based data warehouses include lower costs, limitless storage and compute capabilities, scale on a pay-as-you-go basis, and faster disaster recovery. As an organization, you would opt for a data warehouse when you have massive amounts of data from your operational systems that needs to be readily available for reporting and analysis. Some of the popularly used data warehouses include Teradata Enterprise Data Warehouse Platform, Oracle Exadata, IBM DB2 Warehouse on Cloud, IBM Netezza Performance Server, Amazon Redshift, BigQuery by Google Cloudera's Enterprise Data Hub, and Snowflake Cloud Data Warehouse. A data mart is a subsection of the data warehouse, built specifically for a particular business function, purpose, or community of users. For example, sales or finance groups in an organization accessing data for their quarterly reporting and projections. There are 3 basic types of data marts: dependent, independent, and hybrid data marts. Dependent data marts are a subsection of an enterprise data warehouse. Since a dependent data mart offers analytical capabilities for a restricted area of the data warehouse, it also provides isolated security and isolated performance. Independent data marts are created from sources other than an enterprise data warehouse, such as internal operational systems or external data. Hybrid data marts combine inputs from data warehouses, operational systems, and external systems. The difference also lies in how data is extracted from the source systems, the transformations that need to be applied, and how the data is transported into the mart. Dependent data marts, for example, pull data from an enterprise data warehouse, where data has already been cleaned and transformed. Independent data marts need to carry out the transformation process on the source data since it is coming directly from operational systems and external sources. Whatever the type, the purpose of a data mart is to provide data to users that is most relevant to them when they need it. Accelerate business processes by providing efficient response times. Provide a cost and time-efficient way in which data-driven decisions can be taken. Improve end-user response time, and provide secure access and control. A data lake is a data repository that can store large amounts of structured, semi-structured, and unstructured data in their native format. While a data warehouse stores data that has been cleaned, processed, and transformed for a specific need, you do not need to define the structure and schema of data before loading into the data lake. You do not even need to know all of the use cases for which you will ultimately be analyzing the data. A data lake exists as a repository of raw data in its native format, straight from the source, to be transformed based on the use case for which it needs to be analyzed. Which does not mean that a data lake is a place where data can be dumped without governance. While in the data lake, the data is appropriately classified, protected, and governed. A data lake is a reference architecture that is independent of technology. Data lakes combine a variety of technologies that come together to facilitate agile data exploration for analysts and data scientists. Data lakes can be deployed using cloud object storage, such as Amazon S3, or large-scale distributed systems such as Apache Hadoop, used for processing big data. They can also be deployed on different relational database management systems, as well as NoSQL data repositories that can store very large amounts of data. Data lakes offer a number of benefits, such as the ability to store all types of data, unstructured data such as documents, emails, PDFs, semi-structured data such as JSON, XML, CSV, and logs, as well as structured data from relational databases. The agility to scale based on storage capacity, growing from terabytes to petabytes of data, saving time in defining structures, schemas, and transformations since data is imported in its original format, and the ability to repurpose data in several different ways and wide-ranging use cases. This is extremely beneficial as it is hard for businesses to foresee all the different ways in which you could potentially leverage their data in the future. Some of the vendors that provide technologies, platforms, and reference architectures for data lakes include Amazon, Cloudera, Google, IBM, Informatica, Microsoft, Oracle, SAS, Snowflake, Teradata, and Zeloni. In this video, we learned about some of the capabilities of data mining repositories, such as data warehouses, data marts, and data lakes. While they all have a similar goal, they need to be evaluated within the context of the use case and technology infrastructure for selecting the one that works best for an organization's needs. In this video, we will listen to several data professionals talk about some of the factors they consider while deciding on the most appropriate data repository for their organization.
So there's a number of factors to keep in mind while picking the right database for the job. You need to look at the use case. What is the data repository going to be used for? Is it going to be used for storing structured information, semi-structured or unstructured information? Or do you know beforehand what the schema of the data is? Is there performance requirements? Are you working with data at rest or streaming data or data in motion? Does the data need to be encrypted? What's the volume of data that you're working with? Do you need a big data system? And what are the storage requirements? Does the data need to be updated frequently and accessed frequently? Does it just need to be stored and kept in a vault for a long time and is needed for backup purposes, for example? And then your organization might have certain standards that might have put in place of which databases or which data repositories you're allowed to use for different kinds of tasks. So all of these factors need to be kept in mind.
So when we consider what data repository we want to choose, we look at these factors. We look at what are the kind of capacities that this data repository is supposed to handle. And then we also look at the type of access that we need this for. Do we access it in short intervals or do we run long-running queries on it? Am I using it more for transaction processing or am I using it for analytics or archival purpose or for data warehousing purpose? We also look for compatibility. How compatible this new data repository is with my existing ecosystem of programming languages, tools, and any processes that we have. We also consider the security features this repository gives us. And the most important thing is scalability. We may be happy with its performance today, but is it scalable enough? Can it scale along with the organization?
I don't often get to choose the type of data repository that my organization uses, and very few organizations use one data repository these days. On my team that I work on these days, we have a set of preferred solutions. We have a preferred enterprise relational database. We have a preferred open source relational database for some of the smaller projects and for the microservices. And then we also have a preferred unstructured data source. So those are our three main ones. The important thing is to think about the skills that you have within your organization or that you you want to foster within your organization. And consider the costs of the various solutions. In our case, we have some experts on DB2, so our enterprise database of choice is DB2. However, there are other projects that use different ones. For open source, we've changed that a couple of times. We've gone a couple of different directions with where we really want to be there. And all of these, the hosting platform makes a difference as well, because now it's not just, do I want to use IBM DB2 or do I want to use some other vendor's Microsoft SQL Server or whatever. It's not between those two choices. It's when I do those, do I want to do them on AWS RDS? Maybe I should consider Amazon's Aurora. Maybe I should consider Google's relational offerings. There's so many different choices there that you have to consider. There's the decision of how should the data be stored. There's the decision of how should the data be retrieved. And there's also the decision of where. Those are all very important questions when you're deciding on data storage.
I would say the structure of the data, the nature of the application, and the volume at which the data is getting ingested into your database, all these factors determine the nature of the data source that you should pick. In most cases, a relational database should be enough. However, there will be edge cases where relational databases such as IBM DB2, Oracle, or Postgres won't necessarily do the job for you. In those cases, so depending on the use case, for example, if you're ingesting like gigabytes or terabytes of data per day, then document stores such as MongoDB or wide column stores such as Cassandra might be a good fit for you. At the same time, if you're trying to build a product recommendation engines or trying to show the network of relationships between different people on the social media, then graph data structures such as Neo4j or Apache Tinkerpop would be an ideal fit for you. At the same time, if you're mining through terabytes or petabytes of data for analytics, Hadoop engine with MapReduce would be a good fit for you. So it really boils down to the nature of the application and the volume of the data and the structure of the data before you can pick the right database or data source for your use case.
In this video, we will learn about some of the different tools and processes that work to move data from source to destination systems, such as ETL, or the Extract, Transform, and Load process, ELT, or the Extract, Load, and Transform process, and data pipelines. Now we come to the process that is at the heart of gaining value from data, the Extract, Transform, and Load process, or ETL. ETL is how raw data is converted into analysis-ready data. It is an automated process in which you gather raw data from identified sources, extract the information that aligns with your reporting and analysis needs, clean, standardize, and transform that data into a format that is usable in the context of your organization, and load it into a data repository. While ETL is a generic process, the actual job can be very different in usage, utility, and complexity. Extract is the step where data from source locations is collected for transformation. Data extraction could be through batch processing, meaning source data is moved in large chunks from the source to the target system at scheduled intervals. Tools for batch processing include Stitch and Blendo. Stream processing, which means source data is pulled in real time from the source and transformed while it is in transit and before it is loaded into the data repository. Tools for stream processing include Apache Samza, Apache Storm, and Apache Kafka. Transform involves the execution of rules and functions that convert raw data into data that can be used for analysis. For example, making date formats and units of measurement consistent across all source data, removing duplicate data, filtering out data that you do not need, enriching data, for example, splitting full name to first, middle, and last names, establishing key relationships across tables, applying business rules and data validations. Load is the step where processed data is transported to a destination system or data repository. It could be initial loading, that is, populating all the data in the repository, incremental loading, that is, applying ongoing updates and modifications as needed periodically, or full refresh, that is, erasing contents of one or more tables and reloading with fresh data. Load verification, which includes data checks for missing or null values, server performance, and monitoring load failures, are important because of this process step. It is vital to keep an eye on load failures and ensure the right recovery mechanisms are in place. ETL has historically been used for batch workloads on a large scale. However, with the emergence of streaming ETL tools, they are increasingly being used for real-time streaming event data as well. Some of the popular ETL tools available include IBM InfoSphere Information Server, AWS Glue, Improvato, Skyvia, Hevo, and Informatica Power Center. Now let us look at a variation of the ETL process, the Extract, Load, and Transform, or ELT process. In the ELT process, extracted data is first loaded into the target system, and transformations are applied in the target system. The destination system for an ELT pipeline is most likely a data lake, though it can also be a data warehouse. ELT is a relatively new technology powered by cloud technologies. Why do we need an ELT process? ELT is useful for processing large sets of unstructured and non-relational data. It is ideal for data lakes where transformations on the data are applied once the raw data is loaded into the data lake. The ELT process has several advantages. Since the raw data is delivered directly to the destination system rather than a staging environment, this shortens the cycle between extraction and delivery. ELT paired with a data lake allows you to ingest volumes of raw data as immediately as the data becomes available. Compared to the ETL process, ELT affords greater flexibility to analysts and data scientists for exploratory data analytics. ELT transforms only that data which is required for a particular analysis, so it can be leveraged for multiple use cases. In the ETL process, the entire structure of the data in the warehouse may need to be modified if it is not suited for a new use case. ELT is more suited to work with big data. It is common to see the terms ETL or ELT and data pipelines used interchangeably. And although both move data from source to destination, data pipeline is a broader term that encompasses the entire journey of moving data from one system to another, of which ETL and ELT may be subsets. Data pipelines can be architected for batch processing, for streaming data, and a combination of batch and streaming data. In the case of streaming data, data processing or transformation happens in a continuous flow. This is particularly useful for data that needs constant updating, such as data from a sensor monitoring traffic. A data pipeline is a high-performing system that supports both long-running batch queries and smaller interactive queries. The destination for a data pipeline is typically a data lake, although data may also be loaded to different target destinations, such as another application or a visualization tool. There are a number of data pipeline solutions available, most popular among them being Apache Beam, Airflow, and Dataflow. In this video, we learned about some of the different data movement approaches, the ETL, or Extract, Transform, and Load process, and ELT, the Extract, Load, and Transform process. We also learned about data pipelines, encompassing the complete journey of data from one system to another. Gartner defines data integration as a discipline comprising the practices, architectural techniques, and tools that allow organizations to ingest, transform, combine, and provision data across various data types. The report further explains that data integration has several usage scenarios, such as data consistency across applications, master data management, data sharing between enterprises, and data migration and consolidation. In the field of analytics and data science, data integration includes accessing, queuing, or extracting data from operational systems, transforming and merging extracted data either logically or physically, data quality and governance, and delivering data through an integrated approach for analytics purposes. For example, to make customer data available for analytics, you would need to extract individual customers' information from operational systems such as sales, marketing, and finance. You would then need to provide a unified view of the combined data so that your users can access, query, and manipulate this data from a single interface to derive statistics, analytics, and visualizations. How does a data integration platform relate to ETL and data pipelines? While data integration combines disparate data into a unified view of the data, a data pipeline covers the entire data movement journey from source to destination systems. In that sense, you can use a data pipeline to perform data integration, while ETL is a process within data integration. There is no one approach to data integration. However, modern data integration solutions typically support the following capabilities: an extensive catalog of pre-built connectors and adapters that help you connect and build integration flows with a wide variety of data sources such as databases, flat files, social media data, APIs, CRM, and ERP applications. Open source architecture that provides greater flexibility and avoids vendor lock-in. Optimization for both batch processing of large-scale data and continuous data streams, or both. Integration with big data sources. Support for big data is increasingly driving the decision regarding choice of integration platforms. Additional functionalities. For example, specific demands around data quality and governance, compliance, and security. Portability, which ensures that as businesses move to cloud models, they should be able to run their data integration platforms anywhere. And data integration tools are able to work natively in a single cloud, multi-cloud, or hybrid cloud environment. There are many data integration platforms and tools available in the market, ranging from commercial off-the-shelf tools to open-source frameworks. IBM offers a host of data integration tools targeting a range of enterprise integration scenarios, such as InfoSphere Information Server, Cloud Pak for data, IBM Cloud Pak for integration, IBM Data Replication, IBM Data Virtualization Manager, IBM InfoSphere Information Server on Cloud, and IBM InfoSphere Data Stage. Talon's data integration tools include Talon Data Fabric, Talon Cloud, Talon Data Catalog, Talon Data Management, Talon Big Data, Talon Data Services, and Talon Open Studio. SAP, Oracle, Denodo, SAS, Microsoft, Kulik, and Tibco are some of the other vendors that offer data integration tools and platforms. Examples of open-source frameworks include Dell Boomi, Jitterbit, and SnapLogic. There are a significant number of vendors who are offering cloud-based integration platform as a service, or iPaaS, as a hosted service via virtual private cloud or hybrid cloud, such as the Adeptia Integration Suite, Google Cloud's Cooperation 534, IBM's Application Integration Suite on Cloud, and Informatica's Integration Cloud. The data integration space continues to evolve as businesses embrace newer technologies and as data grows, be it in the variety of sources or its use in business decision-making. In this video, we will listen to data professionals talk about some of the data engineering tools, databases, and data repositories they work with.
The ecosystem of data engineering is very, very vast. We work especially mostly with open source tools So we work with RDBMS databases like MySQL. We work with NoSQL databases like MongoDB, Cassandra, graph databases like Neo4j. Python is pretty much indispensable. So whatever feature we feel missing in our data engineering space, we first try to use Python to get that into place, and then over a period of time we see if any product can take its place. We also work with tools like Apache Airflow to create data pipelines. We work with tools like Spark for big data processing. We work with Kafka to handle streaming data. We work with Talend for ETL functionality. We also work with tools like Beautiful Soup and Scrappy for web scraping. And we also look at a variety of cloud storages for our archival and then for our daily storage purposes.
Before Coursera, I worked in a non-profit where SQL Server was the data repository, and we use SQL Server integration service as well as Workato to do data integration. And in Coursera, AWS Redshift is our data warehouse, and we use AWS S3 as our data lake. We have an internal tool to do to build our ETL pipeline and schedule our ETL pipeline. But now we are moving to use an open source tool called Apache Airflow to do our data orchestration.
I worked with relational databases such as IBM DB2, PostgreSQL, and Microsoft SQL Server, and I also have exposure to working on NoSQL database such as Cassandra and MongoDB, and I worked on streaming technologies for replication such as WebSphere and also for backend processing by moving the transactional data by using the Kafka queues onto the back office databases. At the same time, I also worked on data engineering tools or data movement tools for moving data from one data source to another. For example, I worked on SSIS by building these data movement packages. At the same time, I also worked on this cool tool called NiFi. I think it's this NiFi is now maintained by Apache Foundation, which is an open source foundation, which I highly recommend looking at some of their projects because they're all open source. The code is open. You can go through the source code and learn a lot about some of these products and even projects. And you can, if you're enthusiastic and have a lot of time on your hands, you can even contribute to some of these projects. I digress, but NiFi can be used to move data between heterogeneous data sources, and I also developed my own scripts such as Shell and Perl and written Java APIs to move data between different applications and vendors.
So most people, myself included, who've done work in data engineering have had to work with a number of databases and tools. Having spent a good part of my data career at IBM, I had to do a lot of work with the IBM DB2 database and later became a product manager for it. But I've also had to work with other databases like MySQL and Postgres. And then as part of my job evolved, I had to pick up skills in big data systems like Hadoop and Spark. So it's important that as a data engineering, a field that continues to evolve, you need to, come up with, you need to become a lifelong learner and keep picking up skills that are going to be required for your job and the problems that you're trying to solve. So as long as you're good with data fundamentals, you should be able to quickly pick up these new skills and technologies.
The primary product that I've worked with my entire career is IBM's DB2 on mid-range platforms, so on Linux, Unix, and Windows. To me, this is a great choice in the relational database space. I also work very heavily with AWS products. I've been working with databases on RDS, Microsoft SQL Server. We've done a little bit of MariaDB there. We also do MariaDB outside of that on our own servers. Those are the primary relational database products that we work with. There are a ton of other tools we work with in order to properly manage those or to manage workflows around those. Of course, GitHub or Git, you have to be familiar with those. Those are integral to any process in a DevOps organization or in most non-DevOps organizations at this point. Using Jenkins, we use Jenkins for a lot of things, to spin up containers, to do maintenance jobs, to manage code deploys. There's a lot of important stuff that we do with Jenkins as well. We use Liquibase. Liquibase is actually excellent. We use it with containers to very easily have some management of the changes that are made to our database schemas.
In this digital world, everyone leaves a trace. From our travel habits to our workouts and entertainment, the increasing number of internet-connected devices that we interact with on a daily basis record vast amounts of data about us. There's even a name for it: big data. Ernst & Young offers the following definition. Big data refers to the dynamic, large, and disparate volumes of data being created by people, tools, and machines. It requires new, innovative, and scalable technology to collect, host, and analytically process the vast amount of data gathered in order to derive real-time business insights that relate to consumers, risk, profit, performance, productivity management, and enhanced shareholder value. There is no one definition of big data, but there are certain elements that are common across the different definitions, such as velocity, volume, variety, veracity, and value. These are the V's of big data. Velocity is the speed at which data accumulates. Data is being generated extremely fast in a process that never stops. Near or real-time streaming, local, and cloud-based technologies can process information very quickly. Volume is the scale of the data, or the increase in the amount of data stored. Drivers of volume are the increase in data sources, higher resolution sensors, and scalable infrastructure. Variety is the diversity of the data. Structured data fits neatly into rows and columns in relational databases, while unstructured data is not organized in a predefined way, like tweets, blog posts, pictures, numbers, and video. Variety also reflects that data comes from different sources: machines, people, and processes, both internal and external to organizations. Drivers are mobile technologies, social media, wearable technologies, geotechnologies, video, and many, many more. Veracity is the quality and origin of data and its conformity to facts and accuracy. Attributes include consistency, completeness, integrity, and ambiguity. Drivers include cost and the need for traceability. With the large amount of data available, the debate rages on about the accuracy of data in the digital age. Is the information real or is it false? Value is our ability and need to turn data into value. Value isn't just profit. It may have medical or social benefits, as well as customer, employee, or personal satisfaction. The main reason that people invest time to understand big data is to derive value from it. Let's look at some examples of the V's in action. Velocity. Every 60 seconds, hours of footage are uploaded to YouTube, which is generating data. Think about how quickly data accumulates over hours, days, and years. Volume. The world population is approximately 7 billion people, and the vast majority are now using digital devices, mobile phones, desktop and laptop computers, wearable devices, and so on. These devices all generate, capture, and store data, approximately 2.5 quintillion bytes every day. That's the equivalent of 10 million Blu-ray DVDs. Variety. Let's think about the different types of data: text, pictures, film, sound, health data from wearable devices, and many different types of data from devices connected to the Internet of Things. Veracity. 80% of data is considered to be unstructured, and we must devise ways to produce reliable and accurate insights. The data must be categorized, analyzed, and visualized. Data scientists today derive insights from big data and cope with the challenges that these massive data sets present. The scale of the data being collected means that it's not feasible to use conventional data analysis tools. However, alternative tools that leverage distributed computing power can overcome this problem. Tools such as Apache Spark, Hadoop, and its ecosystem provides ways to extract, load, analyze, and process the data across distributed compute resources, providing new insights and knowledge. This gives organizations more ways to connect with their customers and enrich the services they offer. So next time you strap on your smartwatch, unlock your smartphone, or track your workout, remember your data is starting a journey that might take it all the way around the world through big data analysis and back to you.
The big data processing technologies provide ways to work with large sets of structured, semi-structured, and unstructured data so that the value can be derived from big data. In some of the other videos, we discussed big data technologies such as NoSQL databases and data lakes. In this video, we are going to talk about 3 open source technologies and the role they play in big data analytics: Apache Hadoop, Apache Hive, and Apache Spark. Hadoop is a collection of tools that provides distributed storage and processing of big data. Hive is a data warehouse for data query and analysis built on top of Hadoop. Spark is a distributed data analytics framework designed to perform complex data analytics in real time. Hadoop, a Java-based open source framework, allows distributed storage and processing of large datasets across clusters of computers. In Hadoop distributed system, a node is a single computer, and a collection of nodes forms a cluster. Hadoop can scale up from a single node to any number of nodes, each offering local storage and computation. Hadoop provides a reliable, scalable, and cost-effective solution for storing data with no format requirements. Using Hadoop, you can incorporate emerging data formats such as streaming audio, video, social media sentiment, and clickstream data, along with structured, semi-structured, and unstructured data not traditionally used in a data warehouse. Provide real-time, self-service access for all stakeholders. Optimize and streamline costs in your enterprise data warehouse by consolidating data across the organization and moving cold data, that is, data that is not in frequent use, to a Hadoop-based system. One of the 4 main components of Hadoop is Hadoop Distributed File System, or HDFS, which is a storage system for big data that runs on multiple commodity hardware connected through a network. HDFS provides scalable and reliable big data storage by partitioning files over multiple nodes. It splits large files across multiple computers, allowing parallel access to them. Computations can, therefore, run in parallel on each node where data is stored. It also replicates file blocks on different nodes to prevent data loss, making it fault-tolerant. Let's understand this through an example. Consider a file that includes phone numbers for everyone in the United States. The numbers for people with last names starting with an A might be stored on server 1, B on server 2, and so on. With Hadoop, pieces of this phone book would be stored across the cluster. To reconstruct the entire phone book, your program would need the blocks from every server in the cluster. HDFS also replicates these smaller pieces into 2 additional servers by default, ensuring availability when a server fails. In addition to higher availability, this offers multiple benefits. It allows the Hadoop cluster to break up work into smaller chunks and run those jobs on all servers in the cluster for better scalability. Finally, you gain the benefit of data locality, which is the process of moving the computation closer to the node on which the data resides. This is critical when working with large datasets because it minimizes network congestion and increases throughput. Some of the other benefits that come from using HDFS include fast recovery from hardware failures, because HDFS is built to detect faults and automatically recover. Access to streaming data, because HDFS supports high data throughput rates. Accommodation of large datasets, because HDFS can scale to hundreds of nodes or computers in a single cluster. Portability, because HDFS is portable across multiple hardware platforms and compatible with a variety of underlying operating systems. Hive is an open-source data warehouse software for reading, writing, and managing large dataset files that are stored directly in either HDFS or other data storage systems such as Apache HBase. Hadoop is intended for long sequential scans, and because Hive is based on Hadoop, queries have very high latency, which means Hive is less appropriate for applications that need very fast response times. Also, Hive is read-based and therefore not suitable for transaction processing that typically involves a high percentage of write operations. Hive is better suited for data warehousing tasks such as ETL, reporting, and data analysis, and includes tools that enable easy access to data via SQL. This brings us to Spark, a general-purpose data processing engine designed to extract and process large volumes of data for a wide range of applications, including interactive analytics, streams processing, machine learning, data integration, and ETL. It takes advantage of in-memory processing to significantly increase the speed of computations and spilling to disk only when memory is constrained. Spark has interfaces for major programming languages, such as Java, Scala, Python, R, and SQL. It can run using its standalone clustering technology, as well as on top of other infrastructures such as Hadoop. And it can access data in a large variety of data sources, including HDFS and Hive, making it highly versatile. The ability to process streaming data fast and perform complex analytics in real time is the key use case for Apache Spark. In this video, we will listen to several data professionals talk about the impact of big data on data engineering.
So how is big data changing and shaping the field of data engineering? Big data can be described as the data that has these 4 characteristics, also known as 4 V's: velocity, veracity, volume, and variety.
Big data has had a major impact on data engineering, making it a much more diverse and a rich field. It's quite natural because with all the data that the organizations are collecting these days, being able to make sense of it and derive insights from it is becoming more and more relevant and critical. And that has opened up a vast opportunity. Not only have we seen the emergence of new technologies and products related to working with big data, it's also created a huge demand for professionals who can effectively work with large volumes and variety of data, both for building and managing these big data systems, but also for analyzing data within them.
In the pre-IoT and social media days, the number of ways you can ingest the data into a database are really small. Like, for example, you have a data entry analyst that's putting data into these databases at a very slow pace. but in the past decade, especially with these all new gadgets and devices talking to each other on these APIs, pushing latest updates to these different gadgets, the nature of the data itself changed. As a result of this evolution, the data engineering evolved as well, because your traditional DBMSs are not a one-size-fits-all solution like a lot of database administrators and data engineers discovered in a hard way. With these variety of data sources and volumes, the field of data engineering itself evolved significantly, and data engineers ended up inventing these new data sources such as Google Bigtable, Cassandra, graph databases, Hadoop, MapReduce to analyze these petabytes of data. So data engineers ended up writing their own tools and also learning and working on new technologies. So there was a big evolution due to the big data.
Big data has fundamentally changed things in that organizations are much more accepting of storing large amounts of data. Storage for data, actual disk space, is no longer a big issue. We've gotten to the point where we've stored a lot more data. And that's what the big data buzzword storm has really brought about. That and better ways of handling large amounts of data. You know, it's we can think of big data in different ways. There's obviously unstructured data, which has become a huge thing and is usually not handled within databases. If it is, it's handled in something like MongoDB. And then there's also just the vast amount more of data that we're dealing with.
In this video, we will learn about the layers of a data platform architecture. A layer represents functional components that perform a specific set of tasks in the data platform. The layers that we are going to explore include data ingestion or data collection layer, data storage and integration layer, data processing layer, and analysis and user interface layer. We will also learn about the data pipeline layer, which overlays multiple layers. The data collection layer is responsible for connecting to the source systems and bringing the data from these systems into the data platform. This layer performs the following key tasks: connect to data sources, transfer data from these data sources to the data platform in streaming, batch, or both modes, and maintain information about the data collected in the metadata repository. For example, how much data was ingested in a batch, data source, and other descriptive information. Google Cloud Data Flow, IBM Streams, IBM Streaming Analytics on Cloud, Amazon Kinesis, and Apache Kafka are some of the tools used for data ingestion, supporting both batch and streaming modes. Once data is ingested, it needs to be stored and integrated. The storage and integration layer in a data platform needs to store data for processing and long-term use, transform and merge extracted data either logically or physically, and make data available for processing in both streaming and batch modes. The storage layer needs to be reliable, scalable, high-performing, and cost-efficient. IBM DB2, Microsoft SQL Server, MySQL, Oracle Database, and PostgreSQL are some of the popular relational databases. Cloud-based relational databases, also referred to as database as a service, have gained great popularity over the recent years, such as IBM DB2 on Cloud, Amazon Relational Database Service, or RDS, and Google Cloud SQL and SQL Azure. In the NoSQL, or non-relational database systems on cloud, we have IBM Cloudant, Redis, MongoDB, Cassandra, and Neo4j. Tools for integration include IBM's Cloud Pak for Data and Cloud Pak for Integration, Talon's Data Fabric, and OpenStudio. Open source tools such as Dell Boomi and SnapLogic are also very popular integration tools. There are a number of vendors offering cloud-based integration platform as a service, or iPaaS. For example, Adeptia Integration Suite, Google Cloud's Cooperation 534, IBM's Application Integration Suite on Cloud, and Informatica's Integration Cloud. Once the data has been ingested, stored, and integrated, it needs to be processed. Data validations, transformations, and applying business logic to the data are some of the things that need to happen in this layer. The processing layer should be able to read data in batch or streaming modes from storage and apply transformations, support popular querying tools and programming languages, scale to meet the processing demands of a growing dataset, and provide a way for analysts and data scientists to work with data in the data platform. Some of the transformation tasks that occur in this layer include structuring, essentially actions that change the form and schema of the data. This change may be as simple as changing the order of fields within a record or dataset, or as complex as combining fields into complex structures using joins and unions. Normalization, which focuses on cleaning the database of unused data and reducing redundancy and inconsistency. Denormalization, which combines data from multiple tables into a single table so that it can be queried more efficiently for reporting and analysis. And data cleaning, which fixes irregularities in data to provide credible data for downstream applications and uses. There are a host of tools available for performing these transformations on data, selected based on the data size, structure, and specific capabilities of the tool, such as spreadsheets, OpenRefine, Google Data Prep, Watson Studio Refinery, and Trifacta Wrangler. Python and R also offer several libraries and packages that are explicitly created for processing data. It is important to note that storage and processing may not always be performed in separate layers. For example, in relational databases, storage and processing can occur in the same layer, while in big data systems, data can be first stored in the Hadoop File Distribution System, or HDFS, and then processed in a data processing engine like Spark. And the data processing layer can also precede the data storage layer, where transformations are applied before the data is loaded or stored in the database. The analysis and user interface layer delivers processed data to data consumers. Data consumers can include business intelligence analysts and business stakeholders who consume this data through interactive visual representations, such as dashboards and analytical reports. Data scientists and data analysts that further process this data for specific use cases, and other applications and services that may need this data as input for further use. The analysis and UI layer needs to support querying tools and programming languages. For example, SQL for querying relational databases, and SQL-like querying tools for non-relational databases, such as CQL for Cassandra. Programming languages such as Python, R, and Java. APIs that can be used to run reports on data for both online and offline processing. APIs that can consume data from the storage in real time for use in other applications and services. And dashboarding and business intelligence applications. For example, IBM Cognos Analytics, Tableau, Jupyter Notebooks, Python and R libraries, and Microsoft Power BI. Overlaying the data ingestion, data storage and integration, and data processing layers is the data pipeline layer with the extract, transform, and load tools. This layer is responsible for implementing and maintaining a continuously flowing data pipeline. There are a number of data pipeline solutions available, most popular among them being Apache Airflow and Dataflow. In this video, you learned about the layers of a data platform architecture. This is a simplified rendition of a complex architecture that supports a broad spectrum of tasks. A data store or data repository is a general term used to refer to data that has been collected, organized, and isolated so that it can be used for business operations or mined for reporting and data analysis. A repository can be a database, data warehouse, data mart, big data store, or a data lake. A well-designed data repository is essential for building a system that is scalable and capable of performing during high workloads. In this video, we will look at some of the primary considerations for designing a data store, such as the type of data you want to store, volume of data, intended use of data, storage considerations, and privacy, security, and governance needs of your organization. There are multiple types of databases, and selecting the right one is a crucial part of designing. A database is essentially a collection of data designed for the input, storage, search and retrieval, and modification of data. Depending on the type of data, databases can be categorized in two primary ways: relational and non-relational. Relational databases, or RDBMSs, are best used for structured data, which has a well-defined schema and can be organized into a tabular format. Non-relational databases, or NoSQL, are best for semi-structured and unstructured data, that is, schemaless and free-form data. Non-relational databases, based on the type of data and how you want to query the data, are of four different types: key value, document, column, and graph-based. If you're looking to run complex search queries and multi-operation transactions, for example, a document-based database may not be the best option for you. Like, you would not opt for a graph-based database if you need to process high-volume transactions, because graph-based databases are not optimized for large-volume analytics queries. Another important consideration that goes into the design of a data store is the volume or scale of data. When you need to store large volumes of raw data in its native format, straight from its source, a data lake would be the appropriate choice for you. With a data lake, you can store both relational and non-relational data at scale without defining the data's structure and schema. Or when you're dealing with big data, that is, data that is not only high volume, but also high velocity, of diverse types, and needs distributed processing for fast analytics, then a big data repository would be an option you would explore. Big data stores split large files across multiple computers, allowing parallel access to them. Computations run in parallel on each node where data is stored. How you intend to use the data you are collecting is also an important consideration for the choice and design of a data store. The number of transactions, frequency of updates, type of operations performed on the data, response time, and backup and recovery requirements all need to be provisioned for in the design of a data store. Whether you need to use the data store for recording high-volume transactional data or executing complex queries for analytical purposes, your processing and storage needs will differ. Transactional systems, that is, systems used for capturing high-volume transactions, need to be designed for high-speed read, write, and update operations. Analytical systems, on the other hand, need complex queries to be applied to large amounts of historical data aggregated from transactional systems. They need faster response times to complex queries. Schema design, indexing, and partitioning strategies have a big role to play in performances of systems based on how data is getting used. The intended use of data also drives scalability as a design consideration. Scalability of a data store is its capability to handle growth in the amount of data, workloads, and users. Normalization of the database is another important consideration at the design stage. Normalization is the process of efficiently organizing data in a database. Done right, it helps in the optimal use of storage space, makes database maintenance easier, and provides faster access to data. Normalization is important for systems that handle transactional data, but for systems designed for handling analytical queries, normalization can lead to performance issues. Now we'll look at some key design considerations from the perspective of storage. These are performance, availability, integrity, and recoverability of data. Performance parameters include throughput and latency. That is, the rate at which information can be read from and written to the storage, and the time it takes to access a specific location in storage. Availability. Your storage solution must enable you to access your data when you need it, without exception. There should be no downtime. Integrity. Your data must be safe from corruption, loss, and outside attack. And recoverability. Your storage solution should ensure that you can recover your data in the event of failures and natural disasters. A secure data strategy is a layered approach. It includes access control, multi-zone encryption, data management, and monitoring systems. Regulations such as GDPR, CCPA, and HIPAA restrict the ownership, use, and management of personal and sensitive data. Data needs to be made available through controlled data flow and data management by using multiple data protection techniques. This is an important part of a data store design. Strategies for data privacy, security, and governance regulations need to be a part of a data store's design from the start. Done at a later stage, it results in patchwork. In this video, we learned about some of the considerations that guide the design of a data store. Enterprise-level data platforms and data repositories need to tackle security at multiple levels. In this video, we will learn about the various facets of security as it applies to data platforms and data lifecycle management. These include physical infrastructure security, network security, application security, and data security. Let us first look at the three key components to creating an effective strategy for information security in general. These are popularly referred to as the CIA triad. The C in this triad stands for confidentiality through controlling unauthorized access. I for integrity through validating that your resources are trustworthy and have not been tampered with. And A is for availability, by ensuring authorized users have access to resources when they need it. The CIA triad is applicable to all facets of security, be it infrastructure, network, application, or data security. Now we'll look at the four different facets or levels of security. The first level is physical infrastructure security. A key component of security for an IT system is the security of the physical infrastructure and facilities that house the system. In the case of cloud computing, this extends to the cloud service provider's infrastructure and facilities. Here are some of the measures that are taken to ensure physical infrastructure security. Access to the perimeter of the facility based on authentication and round-the-clock surveillance for entry and exit points. Multiple power feeds from independent utility providers with dedicated generators and UPS battery backup. Heating and cooling mechanisms for managing the temperature and humidity levels in the facility. And by factoring in environmental threats before considering the location of the facility. For example, infrastructure facilities are never housed in floodplains. In areas prone to earthquakes, the infrastructure is housed in an earthquake-resistant structure. Multi-level lightning protection and earthing systems are also installed in such facilities. The next level is network security. Network security is vital to keep interconnected systems and data safe. Network security solutions include firewalls to prevent unauthorized access to private networks that are connected to the internet, network access control to ensure endpoint security by allowing only authorized devices to connect to the network. For example, a corporate network may not allow devices with outdated service packs to connect to their network. Network segmentation to create silos, or virtual local area networks, within a network so that you can segregate your assets into individual silos based on the level of security required for different assets. Security protocols to ensure attackers cannot tap into data while it is in transit. And intrusion detection and intrusion prevention systems that inspect incoming traffic for intrusion attempts and vulnerabilities. The third dimension of security is application security. Application security is critical for keeping customer data private and ensuring applications are fast and responsive. Security needs to be built into the foundation of an application in order to prevent other applications and services from introducing vulnerabilities. You can make your application safe by following security engineering practices such as threat modeling to identify relative weaknesses and attack patterns related to the application, secure design that mitigates risks, secure coding guides and practices that prevent vulnerabilities, and security testing to fix problems before the application is deployed and to validate that it is free from known security issues. And the fourth and final dimension is data security. Data is either at rest in storage or in transit between systems, applications, services, and workloads. Be it at rest or in motion, data needs to be protected. One of the primary controls for data security is to enable access to data through a system of authentication and authorization. Authentication systems verify that you are who you say you are, and they accomplish this using passwords, tokens, biometrics, or a combination of these. Authorization ensures that users access information based on their roles and the privileges assigned to their roles. Data at rest includes files, objects, and storage. This type of data is stored physically, such as in a database, data warehouse, tapes, off-site backups, or on mobile devices. Organizations can use encryption to fight threats to their data at rest. Encrypting data protects information from disclosure, even if that information is lost or intercepted. Data that is moving from one place to another, such as when it is transmitted over the internet, is referred to as data in transit or data in motion. Encryption methods such as HTTPS, SSL, and TLS are often used to protect data in motion. Later on in the course, you will learn more about the different stages of data lifecycle, the vulnerabilities data can be exposed to, and the security features that help protect data end-to-end through its lifecycle. It is vital to proactively monitor, track, and react to security violations in time, and for that, you need end-to-end visibility and integration of security processes and tools throughout the enterprise. Security monitoring and intelligence systems create a complete audit history for triage and compliance purposes, and provide reports and alerts that help enterprises react to security violations in time. In this video, you learned about some of the facets of security as it applies to the enterprise level. Every enterprise needs to have a corporate-level security policy that ensures business, IT, and all stakeholders contribute to achieving security goals through people, policy, processes, systems, and tools. In this video, we will listen to several data professionals talk about the importance of data security as it relates to data engineering.
So if your data is not secure, nothing else about it really is going to matter in the long run. There are many companies who are examples of serious data breaches, and while that won't necessarily put you out of business these days, that depends on the size of your organization somewhat to begin with. If you're a smaller organization and you lose access to your own data, that's certainly a potentially company-ending problem. You really can't understate the importance of data security. It's often something we think of, oh, we'll harden it after go live, or we'll harden it just before go live. But really, it's something that you have to be thinking about data security along every step of the way.
The importance of security of data can't be stressed enough. A few years ago, The Economist magazine published an article saying the world's most valuable resource is no longer oil, but data. So if data is the most valuable resource an organization has, it needs to be secured and protected. And failure to do so can have catastrophic consequences. So data security, governance, compliance, these are not just things that a data engineer needs to worry about. This needs to be an important part of not just the data architecture, but the entire organizational processes, and every part of the organization needs to keep on top of these things.
We have to make sure that when we have separate production and non-production environments, that our production data doesn't get unmasked into a lower environment. There are absolutely data breaches that can happen that way. We have to think about making sure that people who have access to production data really need that access to production data. The important thing is to understand the security levels and roles for the tool you're using and make sure that each user is getting the least privilege they need in order to do their jobs. It's when we give people more access that we really open things up to data breaches and data security problems. Most of the threats to your data are actually more likely to come from within your organization than without. It's it may be exciting or whatever to think of somebody coming from outside of your organization to get to your data, but most often that threat is going to come from inside your organization. A lot of the things that we hear about in the data profession are things like people at prescription drug places accessing the prescriptions of celebrities. There are things along those lines that we have to be very careful in protecting the data. Data is a natural resource these days, right? The world of big data, data is oil, that's our new natural resource. So it's our job to make sure that that financial aspect of valuable data is protected and that our organization is not at risk for being in the news as one of those causing a data breach, or even worse, being put out of business because of a data breach. I consider part of data security the ability to restore my data and the ability to recover if a particular set of hardware fails. To me, that's part of security, because if we lose the data because of a hardware failure, that means we don't have access to the data, which is part of data security in my own estimation.
In this video, we will learn about the different methods and tools available for gathering data from the data sources discussed earlier in the course, such as databases, the web, sensor data, data exchanges, and several other sources leveraged for specific data needs. We will also learn about importing data into different types of data repositories. SQL, or Structured Query Language, is a querying language used for extracting information from relational databases. SQL offers simple commands to specify what is to be retrieved from the database, the table from which it needs to be extracted, grouping records with matching values, dictating the sequence in which the query results are displayed, and limiting the number of results that can be returned by the query amongst a host of other features and functionalities. Non-relational databases can be queried using SQL or SQL-like query tools. Some non-relational databases come with their own querying tools, such as CQL for Cassandra and GraphQL for Neo4j. Application Programming Interfaces, or APIs, are also popularly used for extracting data from a variety of data sources. APIs are invoked from applications that require the data and access an endpoint containing the data. Endpoints can include databases, web services, and data marketplaces. APIs are also used for data validation. For example, a data analyst may use an API to validate postal addresses and zip codes. Web scraping, also known as screen scraping or web harvesting, is used for downloading specific data from web pages based on defined parameters. Among other things, web scraping is used to extract data such as text, contact information, images, videos, podcasts, and product items from a web property. RSS feeds are another source typically used for capturing updated data from online forums and news sites, where data is refreshed on an ongoing basis. Data streams are a popular source for aggregating constant streams of data flowing from sources such as instruments, IoT devices and applications, and GPS data from cars. Data streams and feeds are also used for extracting data from social media sites and interactive platforms. Data exchange platforms allow the exchange of data between data providers and data consumers. Data exchanges have a set of well-defined exchange standards, protocols, and formats relevant for exchanging data. These platforms not only facilitate the exchange of data, but they also ensure that security and governance are maintained. They provide data licensing workflows, de-identification and protection of personal information, legal frameworks, and a quarantined analytics environment. Examples of popular data exchange platforms include AWS Data Exchange, Crunchbase, Loadame, and Snowflake. Numerous other data sources can be tapped into for specific data needs. For marketing trends and ad spending, for example, research firms like Forrester and Business Insider are known to provide reliable data. Research and advisory firms such as Gartner and Forrester are widely trusted sources for strategic and operational guidance. Similarly, there are many trusted names in the areas of user behavior data, mobile and web usage, market surveys, and demographic studies. Data that has been identified and gathered from various data sources now needs to be loaded or imported into a data repository before it can be wrangled, mined, and analyzed. The importing process involves combining data from different sources to provide a combined view and a single interface, using which you can query and manipulate the data. Depending on the data type, the volume of data, and the type of destination repository, you may need varying tools and methods. Specific data repositories are optimized for certain types of data. Relational databases store structured data with a well-defined schema. If you're using a relational database as the destination system, you will only be able to store structured data, such as data from OLTP systems, spreadsheets, online forms, sensors, network and web logs. Structured data can also be stored in NoSQL. Semi-structured data is data that has some organizational properties, but not a rigid schema, such as data from emails, XML, zipped files, binary executables, and TCP or IP protocols. Semi-structured can be stored in NoSQL clusters. XML and JSON are commonly used for storing and exchanging semi-structured data. JSON is also the preferred data type for web services. Unstructured data is data that does not have a structure and cannot be organized into a schema, such as data from web pages, social media feeds, images, videos, documents, media logs, and surveys. NoSQL databases and data lakes provide a good option to store and manipulate large volumes of unstructured data. Data lakes can accommodate all data types and schema. ETL tools and data pipelines provide automated functions that facilitate the process of importing data. Tools such as Talend and Informatica and programming languages such as Python and R and their libraries are widely used for importing data. Raw data has to undergo a series of transformations and cleansing activities in order to be analytics ready. Data wrangling, also known as data munging, is an iterative process that involves data exploration, transformation, validation, and making data available for credible and meaningful analysis. It includes a whole range of transformations and cleansing activities, some of which we will learn about in this video. Now, let us look at some of the key transformations that data typically undergoes in a data analytics scenario. Let's begin with the first transformation task, structuring. This task includes actions that change the form and schema of your data. The incoming data can be in varied formats. You might, for example, have some data coming from a relational database and some data from web APIs. In order to merge them, you will need to change the form or schema of your data. This change may be as simple as changing the order of fields within a record or dataset, or as complex as combining fields into complex structures. Joins and unions are the most common structural transformations used to combine data from one or more tables. How they combine the data is different. Joins combine columns. When two tables are joined together, columns from the first source table are combined with columns from the second source table in the same row. So each row in the resultant table contains columns from both tables. Unions combine rows. Rows of data from the first source table are combined with rows of data from the second source table into a single table. Each row in the resultant table is from one source table or another. Transformation can also include normalization and denormalization of data. Normalization focuses on cleaning the database of unused data and reducing redundancy and inconsistency. Data coming from transactional systems, for example, where a number of insert, update, and delete operations are performed on an ongoing basis, are highly normalized. Denormalization is used to combine data from multiple tables into a single table so that it can be queried faster. For example, normalized data coming from transactional systems is typically denormalized before running queries for reporting and analysis. Another transformation type is cleaning. Cleaning tasks are actions that fix irregularities in data in order to produce a credible and accurate analysis. The first step in the data cleaning workflow is to detect the different types of issues and errors that your dataset may have. You can use scripts and tools that allow you to define specific rules and constraints and validate your data against these rules and constraints. You can also use data profiling and data visualization tools for inspection. Data profiling helps you to inspect the source data to understand the structure, content, and interrelationships in your data. It uncovers anomalies and data quality issues. For example, blank or null values, duplicate data, or whether the value of a field falls within the expected range. Visualizing the data using statistical methods can help you to spot outliers. For example, plotting the average income in a demographic dataset can help you spot outliers. That brings us to the actual cleaning of the data. The techniques you apply for cleaning your dataset will depend on the use case and the type of issues you encounter. Let's look at some of the more common data issues. Let's start with missing values. Missing values are very important to deal with as they can cause unexpected or biased results. You can choose to filter out the records with missing values or find a way to source that information in case it is intrinsic to your use case. For example, missing age data from a demographic study. A third option is a method known as imputation, which calculates the missing value based on statistical values. Your decision on the course of action you choose needs to be anchored in what's best for your use case. You may also come across duplicate data, data points that are repeated in your dataset. These need to be removed. Another type of issue you may encounter is that of irrelevant data. Data that does not fit within the context of your use case can be considered irrelevant data. For example, if you are analyzing data about the general health of a segment of the population, their contact numbers may not be relevant for you. Cleaning can involve data type conversion as well. This is needed to ensure that values in a field are stored as the data type of that field. For example, numbers stored as numerical data type, or dates stored as a date data type. You may also need to clean your data in order to standardize it. For example, for strings, you may want all values to be in lowercase. Similarly, date formats and units of measurement need to be standardized. And there may be syntax errors, for example, white spaces, or extra spaces at the beginning or end of a string is a syntax error that needs to be rectified. This can also include fixing typos or format. For example, the state name being entered as a full form, such as New York, versus an abbreviated form such as NY in some records. Data can also have outliers, or values that are vastly different from other observations in the dataset. Outliers may or may not be incorrect. For example, when an age field in a voter's database has the value 5, you know it is incorrect data and needs to be corrected. Now, let's consider a group of people where the annual income is in the range of $100,000 to $200,000, except for that one person who earns $1 million a year. While the data point is not incorrect, it is an outlier and needs to be looked at. In this video, you learned about some of the transformations and cleansing activities that need to be performed on raw data in order to make it analytics ready. You also learned how data profiling and data visualization help spot the issues that need to be addressed. In this video, we will look at some of the popularly used data wrangling software and tools, such as Excel Power Query or spreadsheets, OpenRefine, Google Data Prep, Watson Studio Refinery, Trifecta Wrangler, Python, and R. Let's begin with the most basic software used for manual wrangling, spreadsheets. Spreadsheets such as Microsoft Excel and Google Sheets have a host of features and inbuilt formulae that can help you identify issues, clean, and transform data. Add-ins are available that allow you to import data from several different types of sources and clean and transform data as needed, such as Microsoft Power Query for Excel and Google Sheets Query Function for Google Sheets. OpenRefine is an open source tool that allows you to import and export data in a wide variety of formats, such as TSV, CSV, XLS, XML, and JSON. Using OpenRefine, you can clean data, transform it from one format to another, and extend data with web services and external data. OpenRefine is easy to learn and easy to use. It offers menu-based operations, which means you don't need to memorize commands or syntax. Google Data Prep is an intelligent cloud data service that allows you to visually explore, clean, and prepare both structured and unstructured data for analysis. It is a fully managed service, which means you don't need to install or manage the software or the infrastructure. Data Prep is extremely easy to use. With every edition that you take, you get suggestions on what your ideal next step should be. Data Prep can automatically detect schemas, data types, and anomalies. Watson Studio Refinery, available via IBM Watson Studio, allows you to discover, cleanse, and transform data with built-in operations. It transforms large amounts of raw data into consumable, quality information that's ready for analytics. Data Refinery offers the flexibility of exporting data residing in a spectrum of data sources. It detects data types and classifications automatically and also enforces applicable data governance policies automatically. Trifecta Wrangler is an interactive cloud-based service for cleaning and transforming data. It takes messy, real-world data and cleans and rearranges it into data tables, which can then be exported to Excel, Tableau, and R. It is known for its collaboration features, allowing multiple team members to work simultaneously. Python has a huge library and set of packages that offer powerful data manipulation capabilities. Let's look at a few of these libraries and packages. Jupyter Notebook is an open-source web application widely used for data cleaning and transformation, statistical modeling, also data visualization. NumPy, or Numerical Python, is the most basic package that Python offers. It is fast, versatile, interoperable, and easy to use. It provides support for large multidimensional arrays and matrices, and high-level mathematical functions to operate on these arrays. Pandas is designed for fast and easy data analysis operations. It allows complex operations such as merging, joining, and transforming huge chunks of data performed using simple single-line commands. Using Pandas, you can prevent common errors that result from misaligned data coming in from different sources. R also offers a series of libraries and packages that are explicitly created for wrangling messy data, such as dplyr, data table, and JSON-Lite. Using these libraries, you can investigate, manipulate, and analyze data. dplyr is a powerful library for data wrangling. It has a precise and straightforward syntax. Data table helps you aggregate large data sets quickly. JSON Lite is a robust JSON parsing tool, great for interacting with web APIs. Tools for data wrangling come with varying capabilities and dimensions. Your decision regarding the best tool for your needs will depend on factors that are specific to your use case, infrastructure, and teams, such as supported data size, data structures, cleaning and transformation capabilities, infrastructure needs, ease of use, and learnability. One of the things query languages help us do is access data in the database so that we can understand it better. In this video, we will learn about some basic querying techniques for analyzing data in a database. These include counting and aggregating your data set, identifying extreme values, slicing data, sorting data, filtering patterns, and grouping data. References to specific functions and operators in this video map to SQL, which we all know is a query language for RDBMSs. However, the querying techniques are applicable to other query languages as well. NoSQL databases, for example, have their own SQL-like query languages, such as Cassandra CQL and Cypher for Neo4j. Also, APIs that can be used to query data. Something very basic that you do when you start with a dataset for analysis is to take stock of how much data you have. In SQL, for example, you can use the count function to count the number of rows or records you have in your dataset. The sample dataset that you now see on your screen includes data for customers who have purchased used cars. In this dataset, there are a total number of 15 records. And if you want to see how many unique car dealers there are in the dataset, you can use the distinct function to isolate the unique car dealers. If you combine count with distinct, you get a count of the total number of unique or distinct car dealers, which in our dataset is 8. Aggregation functions also help to provide an overview of the dataset from different perspectives, such as using the sum function to calculate the sum of a numeric column in a table, using the average function to calculate the average number of a numeric column, and using the stddev function to measure how spread out the numbers are in a data set. In our dataset, for example, we can use the stddev function to see how spread out the cost of a used car is. The average cost for a used car is a little less than $6,000. But if you look at some of the individual rows, you see a significant number of records showing less than $2,000 and just 2 records with $25,000 and above. And the standard deviation is over 11,000. The greater the standard deviation value, the wider the spread. So, as you can see from this example, looking at the standard deviation brings a different perspective to the dataset. The next type of analysis is to identify extreme values in a data column, such as the max function, which gives you the maximum value in a column. For example, the highest amount spent by a customer in our dataset is $37,000. And the min function, which gives you the minimum value in a column, which in our dataset is $1,000. Now, let us say you want to find customers based on a specific condition or set of conditions. Slicing a dataset lets you do that. In this dataset, for example, you would use the slice function if you want to retrieve data for customers who live in a certain area, or who have purchased their car from dealers in a specific area, or those who have spent between $1,000 and $2,000 for their car. You can also use operators that allow you to specify multiple levels. For example, customers who spent between $1,000 and $2,000 on their car and live in a specific area. This brings us to sorting data, which helps to arrange data in a meaningful order, making it easier to understand and analyze. For example, if you want to see if car sales go up around festival time, you can sort the dataset on the date of purchase to see if a large number of sales transactions took place around that time. And you can do this by using the order by function. The order by function also allows you to sort a data column in ascending or descending order. Another powerful querying technique is filtering patterns, which allows us to perform partial matches of data values. Unlike an equal to operator that returns records in which a data value matches a certain value, the like operator helps you to specify a pattern to return records that match a data value partially. In our dataset, for example, let us say we want to filter data for all purchases that happen in a region. The first 3 digits in the PIN codes within this region are constant, but the remaining 2 digits vary for each area within that region. In this case, we can use the like operator to specify the pattern we know we are looking for, which in this case is the first 3 digits, and use wildcard characters for the 4th and 5th digits in the PIN code, since these will be different for each area. Which brings us to another important tool for analysis: grouping data. Grouping of data is performed using the group by statement. For example, you want to find out the total amount spent by customers PIN code-wise. We can use sum and group by to find out the total amount spent by customers grouped by their PIN code. In this video, you learned about some of the querying techniques used for performing some basic but crucial data analysis tasks. One of the key responsibilities of a data engineer is to monitor and optimize systems and data flows for performance and availability. In a data engineering lifecycle, performance can apply to a number of areas. In this video, we will look at some of those areas. Data pipelines encompass the journey of data from source to destination through multiple systems, applications, and processes. A data pipeline typically runs with a combination of complex tools and can face several different types of performance threats, such as scalability in the face of increasing datasets and workloads, application failures, scheduled jobs not starting per schedule, awaiting dependencies, or some tasks not running in correct sequence or not running at all, and tool incompatibilities, since data pipelines consist of a variety of tools handling different tasks. When you need to benchmark or to evaluate performance, you need to have performance metrics. In the case of data pipelines, the performance metrics would include latency, that is, the time it takes for a service to fulfill a request; failures, which is the rate at which a service fails; resource utilization and utilization patterns; and traffic, or number of user requests received in a given period. So, what's the best way to go about troubleshooting performance issues in a data pipeline? It depends on the issue, but generically speaking, these are some of the steps you will probably take. The first step would be to collect as much information about the incident as possible. Most importantly, to ascertain if the observed behavior is actually an issue. The issue could have been reported through an alerting system by a user or flagged during a maintenance check. The next step would be to check if you're working with all the right versions of software and source codes. And in case of any recent deployments, you could check what has changed and investigate if there could be a connection. You would also check the logs and metrics early on in your troubleshooting process to isolate whether an issue is related to infrastructure, data, software, or a combination of these. Error messages in logs and the network load, memory, and CPU utilization at the time of the failure can help with this. But if the logs don't help you isolate the issue, then you'll probably need to reproduce the issue in a test environment. This can be an iterative and time-consuming process. Once you have the root cause hypothesis and have validated the hypothesis through a series of tests, you can plan to take it to production as per your team's process. Another essential dimension of performance tuning is optimizing databases for performance. Let us first understand the performance metrics that need to be monitored in a database. These include system outages, capacity utilization, application slowdown, performance of queries, and conflicting activities and queries being executed based on multiple users giving requests at the same time, and batch activities causing resource constraints. Let us look at some of the best practices for database optimization, such as capacity planning and database design activities, such as indexing, partitioning, and normalization. Capacity planning includes the process of determining the optimal hardware and software resources required for performance, even as the load on the system continues to fluctuate on a day-to-day basis. Capacity planning also factors in future growth requirements. Database indexing helps to quickly locate data without searching each row in a database. It minimizes the number of times a disk needs to be accessed when a query is processed. Database partitioning is another feature that provides multiple performance benefits. It's a process whereby very large tables are divided into smaller individual tables. Queries run faster because they're accessing a smaller part of the data. Partitioning also improves data manageability. Database normalization is a design technique to reduce inconsistencies arising out of data redundancy and anomalies arising out of update, delete, and insert operations on databases. This impacts the efficiency and speed of querying, cleansing, and analyzing operations. Monitoring and alerting systems help us collect quantitative data about our systems and applications in real time. In the data engineering lifecycle, these systems give us visibility into the performance of our data pipelines, platforms, databases, applications, tools, queries, scheduled jobs, and more. Let us look at some of these systems and understand how they work. Database monitoring tools take frequent snapshots of the performance indicators of a database. This can help you track when and how a problem really started to occur. This can help you isolate and get to the root of the issue more efficiently. Application performance management tools help us measure and monitor the performance of applications. They do this by tracking request response time and error messages. These tools also track the amount of resources being utilized by each process, which helps in the proactive allocation of resources to improve application performance. Tools for monitoring the performance of queries gather statistics about query throughput, execution, performance, resource utilization, and utilization patterns for better planning and allocation of resources. Data pipelines typically have long-running processes that take significant time to complete, which also means that the cost of failure is higher when errors are observed or flagged at the end of a process. Job-level runtime monitoring breaks up a job into a series of logical steps which are monitored for completion and time to completion. Monitoring the amount of data being processed through a data pipeline helps to assess if size of the workload could be slowing down a system. Another thing you can do to help you operate your systems at optimal levels is to run maintenance routines. Preventative maintenance routines generate data that we can use to identify systems and procedures responsible for faults and low availability. These routines can be time-based, that is, they can be planned as scheduled activities at pre-fixed time intervals, or condition-based, which means they are performed when there is a specific issue or when a decrease in performance has been noted or flagged. In this video, we learned about some of the aspects of performance tuning and troubleshooting for data pipelines and databases. We also learned about some of the monitoring and alerting systems and maintenance schedules. Data governance is a collection of principles, practices, and processes to maintain the security, privacy, and integrity of data through its life cycle. A data governance framework encompasses every part of an organization's data management process, including technologies, databases, and data models. What are the types of data these regulations seek to protect from misuse? Primarily, personal and sensitive data. That is, data which can be traced back to an individual, can be used to identify the individual, or contains information that can be used to cause harm to the person. For example, data about race, sexual orientation, or genetic information. The General Data Protection Regulation, or GDPR, is a regulation specific to the European Union. It protects the personal data and privacy of EU citizens for transactions that occur within EU member states. In the United States, individual states have formulated their own regulations. For instance, California created the California Consumer Privacy Act, or CCPA, to better protect customer data. There are also industry-specific regulations that govern the collection and use of sensitive and personal data. For example, in healthcare, HIPAA privacy rules govern the collection and disclosure of protected health information. In retail, the PCI DSS standards govern credit card data. And in finance, SOX regulations govern the handling and reporting of financial information. What is compliance? Compliance covers the processes and procedures through which an organization adheres to regulations and conducts its operations in a legal and ethical manner. Organizations need to establish controls and checks in order to comply with regulations, and maintain a verifiable audit trail that can establish their adherence to these regulations. Consequences of noncompliance with the standards can be severe. They can result in financial penalties, mar public perception, and result in loss of trust amongst clients and partners. It is important to mention that compliance is not a one-time activity. It is an ongoing process requiring a blend of people, process, and technology that continues to evolve. Governance regulations require enterprises to know their purpose and be clear and transparent in their actions at every step of the data lifecycle. Let us understand this better by walking through a typical data lifecycle and just a few of the considerations that may apply at each stage. A typical data lifecycle in an organization includes the following stages. In the data acquisition stage, you need to establish what data needs to be collected and the contracts and consent that give you a legal basis for procuring this data. The intended use of this data published as a privacy policy and communicated internally and with individuals whose data is being collected, and the amount of data you need to meet your defined purposes. For example, does the email address meet your purpose, or do you also need to have the phone numbers and PIN codes? In the data processing stage, you will be required to establish the details of how you are going to process personal data and your legal basis for the processing of personal data, such as a contract or consent. In the data storage stage, you will be required to establish where the data will be stored, including specific measures that will be taken to prevent internal and external security breaches. In the data sharing stage, you will establish which third-party vendors in your supply chain may have access to the data you are collecting, as well as how you will hold them contractually accountable to the same regulations you are liable for. In the data retention and disposal stages, you will be required to establish what policies and processes you will follow for the retention and deletion of personal data after a designated time, and how you will ensure that in the case of data deletion, it will be removed from all locations, including third-party systems. At each of these stages, you will be required to maintain an auditable trail of personal data acquisition, processing, storage, access, retention, and deletion. Now let us look at some of the controls made available through different tools and technologies for ensuring compliance to governance regulations. Authentication and access control. Today's platforms offer layered authentication processes, such as a combination of passwords, tokens, and biometrics, to provide foolproof protection against unauthorized access of data. Authentication systems are designed to verify that you are who you say you are. Access control systems ensure that authorized users have access to resources, both systems and data, based on their user group and role. Databases, for example, have the concept of roles and privileges, so only authorized users and applications can access specific objects, such as tables or rows or columns in a database. Encryption and data masking. Using encryption, data is converted to an encoded format that can only be legible once it is decrypted via a secure key. Encryption of data is available both for data at rest, as it resides in the storage systems, and data in transit, as it moves through browsers, services, applications, and storage systems. Data masking provides anonymization of data for downstream processing and pseudonymization of data. Using anonymization, the presentation layer is abstracted without changing the data in the database itself. For example, replacing characters with symbols when they are displayed on the screen. Pseudonymization of data is a de-identification process where personally identifiable information is replaced with artificial identifiers so that a dataset cannot be traced back to an individual's identity. For example, replacing the name with a random value from the name's dictionary. Hosting options in on-premise and cloud systems that comply with the requirements and restrictions for international data transfers. Monitoring and alerting functionalities. Security monitoring helps to proactively monitor, track, and react to security violations across infrastructure, applications, and platforms. Monitoring systems also provide detailed audit reports that track access and other operations on the data. Alerting functionalities flag security breaches as they occur so that immediate remedial actions can be triggered. The alerts are based on the severity and urgency level of the breach, which is predefined in the system. Data erasure. Data erasure is a software-based method of permanently clearing data from a system by overwriting. This is different from a simple deletion of data since deleted data can still be retrieved. In this video, we learned why data governance and compliance, which go hand in hand, are critical through the data lifecycle, and the role tools and technologies play in the governance implementation framework. In this video, we will learn about career opportunities in data engineering. To start with, let's get a high-level view of this job market as cited in some of the popular and credible sources in the industry. According to LinkedIn's 2020 Emerging Jobs Report, data engineering now joins machine learning and data science as one of the top 10 jobs experiencing tremendous growth in the U.S., with industries from retail to automotive taking notice and making this hard-to-hire talent a part of their teams. Dice Tech Job Report of 2020 lists data engineering as the fastest-growing tech occupation with a year-over-year growth of 50%. And with more and more companies competing to find the right talent for their expanding data infrastructure, it is expected to grow even further in years to come. The report goes on to identify healthcare, technology, and consulting as the three fields with the largest need for data science talent as a whole, including data engineering. Though no industry in the coming times, says the report, is going to be untouched by this discipline. Data engineering jobs are listed as one of the top 10 jobs in Glassdoor's Best Jobs in America for 2020. The criteria for the listing includes earning potential, job satisfaction ratings, and number of job openings. There is a wide variety of job roles available for data engineers. Job titles are fluid, and a data engineering role can look a little different in every company. Typically, data engineering roles in organizations tend to break up the specialization into data architecture, database design and architecture, data platforms, data pipelines and ETL, data warehouses, and big data. The roles may all be labeled generically as data engineers or carry specific titles such as data architect, database architect, ETL engineer, data warehouse engineer, and big data engineer. If your organization wants you to focus on implementing and managing a cloud-based data lake, for example, your job title probably will be data lake engineer. But in each of these niche openings, knowledge of operating systems, languages, databases, and infrastructure components, such as virtual machines, networking, and application services, would be a given expectation, as also data's potential application in business. It may also be that you get an opportunity to work on the whole data engineering lifecycle at once, typically in a small team or startup that is just starting to build their data engineering practice. But as the practice grows, a multidisciplinary engineering team would start to take shape. If you are part of an organization that has set up a data engineering practice, then you will likely start your journey as an associate or junior data engineer and work your way up through data engineer, senior data engineer, lead data engineer, and principal data engineer roles. Growing up the ranks could be a bit like navigating a matrix. You will be required to not only expand your skills in your niche, but also branch into other areas of data engineering. For example, from being a data architect to gaining a functional understanding, if not hands-on experience, of data warehouses, data lakes, data pipelines, and the ETL process. Growth in data engineering is characterized not only by the expansive tools and technologies that you understand and can work with, but also how much the big picture you're able to see in the data engineering lifecycle. Your communication skills, your ability to collaborate with diverse technical and business stakeholders, your operational or project management skills all need to be growing progressively in order for you to grow into lead positions. As a lead, you will handle growing responsibilities, such as spending more time on converting business requirements into technical specifications and being the bridge between what business wants and what technical teams develop. You would also be evaluating and weighing in on the tools and platforms that you should be using as a team, as well as gaining greater responsibility for implementing systems, processes, and tools for ensuring data quality, data privacy, and compliance with regulations. Now let us look at a few of the emerging roles in the field. Big data engineers and machine learning engineers are a couple of emerging roles that require specialized skills in addition to basic data engineering. Big data engineers work with big data stores, platforms, and processing tools like Hadoop and Spark. They specialize in the management of big data pipelines and movement and processing of data at scale. Machine learning engineers design and implement machine learning algorithms and work with large data sets of structured and unstructured data. This role is an intersection of data engineering and data science and AI skills. In this video, you learned about some of the career opportunities in the field of data engineering. To grow as a data engineer, you will need to constantly learn and implement new tools and technologies as they emerge. And you will also need to be a curious and aware team member. In this video, we will listen to several data professionals talk about how they got into the field of data engineering.
I started off as a DBA on IBM DB2 or DBMS, and I particularly enjoyed solving performance problems for both OLTP and OLAP databases. As a DBA, I got an opportunity to interact with the web application developers, ETL developers, and business intelligence users, and business users, and a few other groups within the organizations. As our business requirements used to evolve, our need to invest and research other non-RDBMS tools and processes evolved as well. For example, to store our documents, we invested in MongoDB, and then for our 24/7, 365 days availability, highly available application, we started exploring Cassandra. And for our analytical database, we started exploring Hadoop and laid out a standalone cluster and did a POC on it. So all of a sudden, after exploring all these technologies and started working on some of them, I'm a data engineer now, not a DBA anymore.
So I have a somewhat unusual way of getting into data engineering. I think of the two usual ways of getting into data engineering is either starting out in system administration and moving into a data profession, or starting out in development and moving into a data profession. But personally, I graduated college, when I did, I got a job at IBM. My goal on my resume at that point was to be a DBA. I had a very targeted goal to get into a data profession, and I was able to get into that data profession immediately. Within 2 years, I could call myself a competent DBA. Before that, I could call myself a DBA, but maybe a beginner. And so it's a little bit of an unusual way that I got there. I think that might be a little bit more common these days. I think there are more opportunities to go directly there. But there are certain fields in technology that often come with expertise from other fields. One of those is data. Another one of those is often DevOps, where you're coming in with either systems operation experience or development experience or both. There are several fields like that, and I think data is one of them. Data can benefit from either of those, because if you know some of the tenets of systems administration and how to deal with storage and the impact of network time and all of those details, it can be very useful. If on the other hand you know how developers deal with data and what they need out of data or what data scientists need out of data, all of those are very valid areas to come into data engineering from. But it's absolutely an area you can start from scratch. The main thing you're looking for, if you're starting from a college degree or if you're starting from no college degree, you're going to need a basic understanding of information technology, and you're going to need a mentor to help you kind of find the way. If you can find a mentor, that's going to make things a lot more easy, because it can help you know what areas to focus in and what areas to kind of ignore. There are an amazing number of resources out on the web these days to help you. I could go on for half a day just listing some of the sites you can go to and get more information. There are online degrees you can work towards, both undergraduate and graduate level. There's so many opportunities to move in that direction these days that it's just amazing.
So my beginnings in this field go back to doing some simple data entry work as a student. And that's what got me interested in working with data and understanding its power. Although I have a degree in computer engineering, that alone did not get me the job of a data engineer. At that time, we did not have online courses, so I bought some books and learned how to work with databases. And more importantly, I applied what I learned from these books by creating database applications and then doing some volunteer work and some freelance work. So these skills and experience of doing real work with databases is what really helped me get an internship. And then after that, I mostly learned new technologies on the job with occasional training classes. And nowadays, I mostly learn about data technology, the new stuff that comes out, by watching YouTube videos and taking online courses.
It is an interesting journey. After graduating from college, I taught science and geography in middle school for 2 years, and then I spent 3 years doing marketing and recruiting in non-profits, in educational non-profits. After that, I went to graduate school to study non-profits management and information systems. It was in the graduate school I got interested in data. So after graduation, I joined education non-profits in Boston and become a business intelligence analyst there. It was my first data-related full-time job. The learning curve for me was steep, but I really enjoyed it. After working there for 1.5 years, though I was still passionate about education, I started to think about maybe doing something differently outside of the non-profit sector. Yeah, I worked in at that time I had worked in non-profits for almost 7 years. So I started to look for opportunities in education technology companies. I applied for a data scientist position at Coursera, but I got rejected very soon. Luckily, the team at that time was also looking for a data engineering role, and they found that my background might be a potential fit. So they reached out to me and asked me whether I was interested in that position. To be honest, at that time, data engineering was new to me. I I didn't even know what's different between data engineering and business intelligence analysts, and data engineering between data engineering and data scientists. But anyway, I took the opportunity and started the interview process with the team, and luckily I got the job. So in the fall of 2018, I moved from Boston to the Bay Area and started my journey in data engineering at Coursera.
There are various pathways you can explore in order to get into the field of data engineering. We are going to explore some of these pathways in this video. Data engineering is a highly technical field. An academic degree in computer science or engineering will set you off on this path right away. It is true that some of the employers will have this as entry-level criteria. But what is also true is that a lot of data engineers, especially the ones who are coming with some background in coding, are self-taught. There are comprehensive online programs and multi-course specializations available by some of the well-known learning platforms such as Coursera, edX, and Udacity. Their curricula have been designed and delivered by some of the best colleges and technology companies in this space. These courses will expose you to hands-on assignments and real-world projects, which will give you the confidence to venture into this field. You can also earn professional certifications from these courses, which are recognized and valued in today's job market. By now, you have a fair idea of the breadth of subdomains and technical skills within data engineering. So it should be fairly easy for you to select the path that meets your current skill level and aspirations. For example, you may decide to build your skills in pipelines or distributed systems or data architecture to begin with before you venture into the other areas of data engineering. Being clear on your short and long-term goals will help you design a learning path for yourself that will support you on this journey. While there are several different ways in which you can make an entry into this field, your technical abilities will be your mainstay in this profession, along with a broad understanding of the scope and use of data in business. If you are not a graduate, or you are a graduate in a non-related stream, but want to upskill or switch careers, then you too can take the help of professional certifications and other learning resources to gain data engineering skills. For example, you could be an IT support specialist, a software tester, a programmer, or involved in any other technical role in your current job and upskilled to gain these skills. You could also be a statistician, a data analyst, a BI analyst, or any other type of data professional and reskill yourself to get into data engineering. If you have some basic familiarity with coding, you can develop some baseline technical skills that can get you started. For example, programming and query languages, working with different operating systems and databases. Having built some of these skills, you can gain an entry-level job or create some projects which you can add to your portfolio before you start to pursue some of your more advanced skills. Real-world exposure is important to solidify your understanding in this field. As you gain experience applying and processing what you have learned, you can move on to larger teams and companies with more complex data needs and infrastructure. Data engineering is a fast-moving field. If you're curious, open to learning new things, and excited about technology, you will be a great asset to any data engineering team. In this video, we will listen to several data professionals talk about what employers look for in a data engineer.
This is a very tricky question because there is no straight answer to this question. Employers look for an individual who has exposure to a breadth of various data-related technologies. It really varies from job to job or role to role. For example, some roles looks for individuals who has exposure to various kinds of data sources, from relational databases to the NoSQL databases to in-memory databases. or key value stores. And some other roles looks for individuals with heavy experience geared towards the data movement processes. That means they need to be able to work on moving the data from a variety of data sources, from RDBMSs to NoSQL databases, or pulling the data from social media using APIs and loading them into their analytical databases such as Hadoop. Apart from that, they also look for good analytical and problem-solving skills in a data engineer.
When I'm hiring somebody in a data field, there are a number of things I look for. One is I look for somebody who is inquisitive, somebody who doesn't just take the data given to them, but asks additional questions to figure out what direction to take something. One of the primary questions I ask when I'm interviewing for that particular trait is, I say, hey, somebody comes to you, they say the database is slow, what do you do? And I'm not looking for them to say I tune memory, I'm not looking for them to say I look at this metric, I'm looking for them to ask questions and think about different directions the slowness could come from, things like that. So somebody who is inquisitive, somebody who can communicate really well. You're never working in a vacuum as a data professional. And there's a lot of other people that you're going to have to interact with. Somebody with a strong work ethic, somebody who really owns what they work with and what they do. Those are all things that I'm really looking for.
I think it is very company specific. In a big company, data engineer may be able to have a narrow focus. For example, just building ETL pipeline. While in a small startup, a data engineer may need to wear different hats, and the employer would expect the data engineer to have very broad skills. In many cases, I think SQL data modeling and ETL methodologies, as well as programming skills such as Python, are pretty essential ones for data engineering. And besides those technology skills, I believe employers also want to see curiosities, good communications, and love of learning in their data engineers.
Employers look for skills on RDBMS. They look for expertise on NoSQL databases. They see if you have any expertise on schema design. They want to know if you can work on ETL, ELT. They also want to see if you can handle streaming data. They would love you to be able to handle multiple data formats, file formats. They also want to see you to be able to work on or to be able to work with web APIs, data scraping, web scraping, and any kind of even basic data analytical skills are looked for. And most importantly, they look for problem solving, and if you can automate any routine work that has to be done at the workplace.
When I'm looking at technical skills, the technical skills, I'm looking for somebody who's familiar with at least one of the technologies I'm looking for, somebody who has a good starting place to go to learn deeper in that area. If I'm looking at a very senior level position, then I'm looking for very specific technical skills because I have a specific technical need that I need filled. But at a junior level, I'm looking for a general fluency with technology and more soft skills than I am specific technical skills. And some of that is asking them what they've done to learn the field. What have they done to, what courses have they taken? What blogs do they read? What directions are they taking to learn more?
So having the right credential, a degree or a certificate, is a good starting point to get noticed. But you also need to be able to demonstrate that you have the right technical and soft skills and then stand out from the other candidates. So for example, what projects have you worked on? Have you done any technical write-ups, presentations, videos in this field? And then there are soft skills like being able to clearly communicate and articulate your work. Whether you're a good fit with the organization is another thing that we look at. For example, if you're going to be working in a team of people, do you have the skills for good teamwork?
In this video, we will listen to several data professionals talk about the different paths you can take to get into data engineering.
So there's a number of ways of becoming a data engineer. You can get a degree from a college or university in a field like software engineering or computer science, and that's how I did it. But this option can be expensive, and it requires an investment of a number of years of your life. And even then, you will need to likely supplement your skills with beyond what has been taught in school to match the requirements of a real job. But if you already have a degree in another field, or you simply don't have the luxury to invest several years in getting a degree, you can do a shorter diploma program or a boot camp in a physical location, or take online courses and certificate programs, which can be both part-time and full-time. So regardless of the option that you choose, be careful about selecting the right program. Look at its cost, the time it takes to complete, whether it's from a reputed provider, is it the content up to date, and look at the reviews. Talk to people who have completed the program. And also make sure that the program matches your learning style. Are you motivated enough to self-learn online, or do you require some hand-holding?
You can become a data engineer from a variety of existing roles. So if you are a system administrator, that's a good starting point. You can master an OS, a database, and then you can become a data engineer. If you are a database administrator, you're already one step closer to being a data engineer. If you're an automation engineer, if you are good at automating manual tasks, then from that path, you can move into being a data engineer. If you're a data analyst, you already know a lot about data. So that's also a good starting point for you to become a data engineer. If you're a programmer, even from being a programmer, you can move into a data engineer.
You can start as a DBA and transition into the data engineering, which worked pretty well for some of my colleagues and myself. And another path that I can think of is a natural transition into the data engineering is from the EDL development track. Bottom line is a data engineer should be very knowledgeable with the databases and different kinds of data sources and data formats, and use that knowledge to build the data pipelines. And apart from these technical skills and technical track, I think academically, if you have a background with in the computer science and mathematics, I think it will help you greatly. It will reduce your time to become a great data engineer.
So the entire field of data engineering is relatively new. And as I mentioned earlier, different companies also have different requirements for each data engineer. So that basically means there are lots of different ways, different paths you can get into data engineering. I have several colleges at Coursera. They studied computer science at college, and they entered into data engineering directly after graduation. I also have some data engineering friends. They used to be software engineers. Those folks that have very strong technical background before entering into data engineering, but that's not really necessary. You can enter into data engineering without very strong computer science background. So my experience is a good example. I worked many years in non-tech positions in non-profits, so I didn't have a strong background. But I started as a business intelligence analyst in the non-profits, where I honed my skills in SQL, in data modeling and database, and then I entered into data engineering at Coursera.
So the typical paths I see for data engineering are coming in either through a system engineering or a developer side. Those are the typical directions we see. Coming in from a help desk, I tend to like that a little bit just because you get a sense of somebody's work ethic from having come in from that direction. But more often you're going to see somebody who started as a developer or somebody who started as a system administrator.
In this video, we will listen to several data professionals talk about the different paths you can take to get into data engineering.
For folks who want to be data engineers, I want to share two pieces of advice. First, focus on building a strong foundation. Data engineering is a relatively new field, and every year there are lots of new technologies emerging. It is important to learn those new technologies, but as a starting point, I think we should build a strong foundation in SQL, Python, data modeling, and ETL methodologies. Second, paying attention to hands-on experience. Nothing was more in data engineering than hands-on experience. You may think it is hard to get hands-on experience without a full-time job or internship, but it shouldn't be that hard. In data engineering world, there are lots of open source tools or freemium tools with the support of enormous online learning materials. I believe there are many ways you can leverage those tools to do your personal projects and do practice. Having hands-on experience would not only help your resume to stand out in the candidates pool, but would also enable you to tackle a lot of questions during the interview process.
So my first advice to anybody working towards becoming a data engineer would be to practice, to find things that you can do that will give you practice in the area. One of my favorite junior DBAs that I work with used to bring his laptop to me with a VM on it and say, "Hey, break my database." And this was great because I would come up with every different way I had seen a database break, and I would try to simulate it on his laptop, and he would come up with solutions. And man, he was a great troubleshooter for having gone through that, because he had seen a lot of the things that it took me years of experience to actually run into. So any way you can come up with to practice, and that can be coming up with your own project, that can be building a database for something in your life. Another one is to get involved with a professional organization. It's great to get involved with other people who are working in that area and to learn from them.
I give to the aspiring data engineers is learn database internals. If you understand the data structures that power these data sources, that's half the battle of the data engineer. Learn SQL and a programming languages. I would say ideally one procedural language such as shell scripting or PL SQL or a Perl, and an object-oriented programming language, either Java or Python, and a functional programming language such as Scala. Once you gain certain expertise, try to share your knowledge with your peers in the community. For example, share your code in the GitHub public repositories, or start writing articles on LinkedIn, or create your own blog, and work extremely hard when you're relatively young, and stay curious. If you do some of these things, I don't think you'll have any kind of problem getting hired as a data engineer. Data engineers are really in high demand these days.
I would recommend is to think about how you're sharing your knowledge and how you're giving back. I'm a blogger. I write a lot about DB2 and about data in general at datageek.blog. And that is one of the number one things. Even if you've been doing something for as little as 6 months, you may know more about some aspect of that thing than anybody else. So even if you've been working with a product for a very short amount of time, beginner blog entries are great. So it's really important as you're starting your journey in data engineering to share your knowledge and make sure that you are giving back to the data engineering community.
So if you want to become a data engineer, you need to understand one thing. The whole concept of data engineering is a lot of skills. It's a lot of width. You need to master a variety of skills and tools. It can be very overwhelming if you look at all those skills or technologies or tools at once. One RDBMS. Choose any RDBMS that is available to you and you're comfortable with, and you can master one RDBMS. After that, move on to master at least one NoSQL database. It can be MongoDB, Cassandra, Neo4j, React, or Redis. You can also understand concepts like web scraping and also start learning them, and also understand that in the future you will be expected to work with APIs. So APIs is a way using which you can interact with other systems seamlessly.
So the first thing is to build the right skills, get your credentials and certificates, and then demonstrate your expertise in a technology or a product that you enjoy working with and is in demand. Write blog posts, write articles, create some YouTube videos or screencasts and demos. And you don't have to be an expert to be able to do so. One of great ways of learning something is to learn to be able to teach it to others. Join a local networking group or a meetup, not just to learn, but also to meet with other people in the field and share your insights and experiences. Like other technology fields, data engineering is continuously evolving. And so make learning a continuous part of your lifelong process. Keep learning and keep up with the new technologies and approaches to working with data. Wish you all the success on your journey to becoming a data engineer.